Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Before there were suns, there was darkness. In the young universe, long after the first brilliant flash of the Big Bang had faded, an endless night prevailed. No stars pierced the black. No galaxies yet spun their graceful arcs. Imagine a cosmos newborn and unilluminated, a vast expanse of cold gas and silent void, waiting eons for a dawn that had not yet come. Slowly, imperceptibly, the darkness began to fray. Tiny ripples of gravity drew together immense clouds of primordial gas, hydrogen and helium, the simplest elements born out of the Big Bang's afterglow. These clouds swirled and gathered in invisible cradles of matter. As they collapsed inward under their own weight, their cores grew denser and hotter. Millions of years passed in darkness, while deep inside those collapsing globes of gas, pressure and heat mounted toward an inevitable flashpoint. Then, at some moment beyond any witness, light appeared. The first star ignited. In an unseen corner of the cosmos, atoms fused and a newborn sun blazed into existence. For the first time, starlight radiated into the darkness, the first sunrise in the history of the universe. One spark became many as more stars kindled across the heavens. Where once there was perfect night, now pinpoints of light spread like campfires across a dark plain. Like dawn breaking over a primordial landscape, the cosmic dark ages ended. The universe felt the glow of its own making. It's almost impossible to fathom the significance of that moment. Each new star was a beacon pushing back the endless night. Each sunrise, a triumph of light over emptiness. Those first suns were giants, burning bright and brief. They lived fast and died in spectacular blasts, some exploding as supernovae that seeded the next generation of stars. In their ferocious cores, these early suns forged heavier elements, carbon, iron, gold, and when they died, they scattered these riches into space as their final gift. The basic matter of planets and of life itself was thus cast into the cosmic winds, ready to become part of new worlds. Billions of years and countless stars later, in a quiet arm of a spiral galaxy, another cloud of gas and dust began to collapse. It carried in it the atoms of those long-dead stars, ancient stardust that had drifted through space for eons. About 4.6 billion years ago, from this enriched nebula, our sun was born. It wasn't the first star, nor the brightest or the biggest. To the universe it was ordinary, one among billions. But around this young sun swirled a disk of debris that would coalesce into planets. One of them, a small rocky world we now call Earth. For ages, the sun burned on in the silent darkness of space, its brilliance spilling outward, touching everything in its new solar system. At first, that light fell only on barren rock and boiling seas. No living eyes yet existed to witness the dawns and dusks. But the sun's warmth began to transform Earth. In sunlit ponds and shallow seas, simple life took hold, nourished by the star's energy. Tiny organisms learned to capture sunlight and grow. The world turned green with algae, drawing sustenance from the sun, beginning a chain of life powered by sunshine. Eons passed, and under the steady gaze of the sun, life on Earth became more complex. From the oceans crawled creatures onto land, and eventually, some small, clever descendants of those early cells lifted their eyes to the sky. They felt the warmth on their faces and saw a golden disk rise each day. They had no scientific words for it, but they felt its importance in their bones. In time, they would give this life-giving light a name: the sun. The long night of cosmic history had given way to day. Darkness had yielded to a cosmos filled with stars. And under the light of one very special star, thinking beings emerged who could marvel at its radiance. For them, and for all of us, the story of the sun is the story of light and life itself, a story that begins in darkness and blossoms in dawn. From myth to model. For most of human history, the sun was not a ball of gas or a nuclear reactor. It was a god. To our distant ancestors, that brilliant orb in the sky was a mystery worthy of worship and awe. Every sunrise was a blessing, every sunset a drama. Ancient peoples spun stories to explain the sun's daily journey. In Egypt, the sun was Ra, the falcon-headed god who sailed his golden barge across the sky by day and through the underworld at night, to be reborn each dawn. In other cultures, the sun rode in a chariot or was a torch carried by a deity. The Aztecs believed the sun needed human blood to sustain it, offering hearts upon altars so that morning would come again. Nearly every civilization built monuments to track and honor the sun, stone circles, pyramids, and temples aligned with the rising or setting sun on solstices and equinoxes, celebrating its life-giving light. To those who first pondered it, the sun's power was both nurturing and frightening. It brought the warmth of spring and the cruelty of drought. Small wonder that early humans personified the sun, gave it names and personalities, prayed for its return in winter, and feared its eclipse as an ominous omen. The sun ruled the day, and by its position in the sky, people knew when to sow crops or hold festivals. It was the center of their world in spirit, long before we learned it was the center by fact. In myth, the sun was often the highest god, the great light of the heavens. But as human curiosity grew, so did the desire to truly understand this celestial flame beyond myth and magic. Slowly, a shift began, a transition from mythos to model, from divine symbol to physical reality. Ancient astronomers and philosophers started asking, what is the sun, really? How far away is it? Why does it shine? As early as 2,000 years ago, Greek thinker Aristarchus suspected the sun was far larger than Earth and perhaps at the center of all the planets. Another Greek, Anaxagoras, dared to say the sun was not Apollo's chariot at all, but a fiery rock, a blazing sphere governed by nature, not the whims of gods. Such ideas were radical and dangerous. Anaxagoras was reportedly exiled for claiming the sun was a red-hot stone rather than a deity, yet he had lit a spark of understanding. Centuries passed before these ideas took hold. In 1543, Nicholas Copernicus published his heliocentric theory, proposing that the sun, not Earth, sat at the center of the known universe. This shattered old cosmologies and, after much controversy, put the sun in its rightful place as the hub of our solar system. Still, Copernicus could not tell what the sun was made of or how it burned. It took the invention of the telescope and the birth of modern science to pry more secrets from our star. In the early 17th century, Galileo Galilei turned his telescope toward the sun and saw dark spots moving across its face, sunspots, proving the sun was not a perfect, unblemished orb. It had markings and it rotated. This was shocking at the time. The heavens were supposed to be perfect, yet here was the sun, clearly imperfect and changing. Each discovery pulled the sun further from the realm of gods and into the realm of nature. Around the same time, Isaac Newton used a prism to show that sunlight is composed of many colors, revealing that white light hides a rainbow within, a clue that would later help decode the sun's composition. By the 19th century, the question of the sun's power puzzled the greatest scientists. Earth was millions of years old, as evidenced by fossils and geology, but no known fire could burn that long. What fuel fed the sun's endless flame? Some suggested the sun was slowly shrinking, converting gravitational energy into heat and light. This idea, the Kelvin-Helmholtz contraction, implied the sun might shine for tens of millions of years, but Earth appeared older than that, so something still didn't add up. The source of the sun's energy remained a mystery. The breakthrough came in the 20th century. In 1905, Albert Einstein's equation E equals mc2 hinted that mass could be converted to enormous energy. The sun had plenty of mass, so perhaps it was using a tiny bit of its mass as fuel each second. In the 1920s, British astronomer Arthur Eddington proposed that the sun's light comes from fusing hydrogen into helium in its core, releasing energy as heat and light. This was a revolutionary idea. The sun was not burning like coal, it was fusing, a nuclear reaction. In the 1930s, physicist Hans Bethe worked out the specific chain of nuclear fusion reactions, the proton-proton chain, that power the sun. At last, science had an answer to why the sun shines. Our star is a massive nuclear reactor, converting matter into energy in its core. The journey from sun god to scientific model took millennia. Humans went from singing hymns to the dawn to charting the sun's spectrum and deciphering the reactions in its heart. Yet there is beauty in both views. The more we learned, the more wondrous the sun became, not a lesser thing than our ancestors imagined, but something far more complex and powerful. The sun of myth rode the sky to bring light to the world. The sun of science does the same, through laws of physics, more subtle and profound than ancient storytellers could have conceived. Our understanding evolved from poetic imagination to mathematical explanation. In doing so, we didn't banish the sun's magic, we transformed it, finding deeper marvel in the real story of a star that forges daylight from the dance of atoms. The sun, a typical star, uniquely ours. By the light of science, our sun was revealed to be one star among countless others. In cosmic terms, it is utterly ordinary. The sun is a middle-aged, medium-sized star, one of hundreds of billions in our Milky Way galaxy. On a clear night, if you point a telescope at the sky, you can see other stars dotting the darkness, each of them a distant sun. Our ancestors once thought the sun and the stars were different. Now we know they are the same, except for their distance from us. If our sun were transported as far away as the typical stars we see at night, it would fade to a tiny point of light, indistinguishable from the rest. In the grand menagerie of stars, the sun sits comfortably in the middle. It is far from the largest or most luminous. Huge blue giants and red supergiants outshine and outswell it by huge margins. And it's not the smallest or faintest. Countless red dwarfs are much cooler and dimmer. The sun is classified as a G-type main sequence star, sometimes called a yellow dwarf, though its light is actually white. It spans about 1.4 million kilometers across. You could line up 109 Earths edge to edge to match its diameter. Over 1 million Earths could fit inside its volume. It's more massive and brighter than roughly 90% of the stars in our galaxy, because the majority are small red dwarfs. But many stars surpass it. Some stars weigh dozens of times more and shine tens of thousands of times brighter, while others are mere fractions of the sun's mass and barely glow. In essence, our sun is a fairly common sort of star, not an extreme outlier, just a reliable middle-of-the-road star. Yet for us, the sun is anything but ordinary. It is our star, the one that matters to us. All the planets, moons, asteroids, and comets of our solar system are bound in orbit by the sun's gravity. The sun contains 99.8% of all the mass in the solar system. It is truly the heavyweight anchor of our cosmic neighborhood. It's like the nucleus of a family of planets, holding them close through its gravitational pull. If we could step back and view our solar system from afar, we'd see the sun as a brilliant light with tiny dots, planets, dancing around it. The sun's presence dominates. Its gravity guides the planets year after year, millennium after millennium. For Earth, the sun is the source of nearly everything. Every ray of daylight, every gentle sunrise or glorious sunset, every breeze and raindrop, each season's warmth or winter's chill, all orchestrated by this star. We call it the sun, as if it were the only one, because for us, it effectively is. It is the only sun we experience, the star that shapes our days and sustains our life. Other stars exist, but they are remote, their light faint. The sun alone provides the heat to keep our world's water liquid and the light to nurture plants. If the sun were magically extinguished, Earth would freeze solid and life, save perhaps some hardy microbes deep underground, would perish. In that sense, while the sun is typical in the galaxy, it is uniquely precious to us. Without it, Earth would be just another frozen rock drifting in eternal night. Our sun is the center of our solar system in both a physical and conceptual sense. The word solar comes from sol, the Latin name for the sun, underscoring that the sun's influence defines our cosmic home. All planets and creatures here owe allegiance to the sun's light. It may be one star among billions, but it's our star, the star that smiles on us each morning. In a universe full of stars, this one is special to Earth. It's the one that gave us life, that daily paints our sky blue and our clouds gold. In that way, the sun will always be extraordinary to us, no matter how common such stars might be from a broader cosmic perspective. What is a star? Birth of a stellar flame. So, what exactly is a star? In simplest terms, a star is a massive glowing ball of gas held together by its own gravity, producing light and heat through nuclear fusion in its core. But this dry description hardly captures the drama of how a star comes to be and how it survives. To truly understand, we must venture into the stellar nurseries where stars are born and witness the delicate balance that keeps them shining for eons. Stars are born in darkness. Imagine a vast interstellar cloud, a nebula, made of cold hydrogen gas mixed with cosmic dust. In some quiet corner of our galaxy, one of these clouds begins to fragment and collapse under its own gravity. Perhaps a nearby supernova's shockwave nudges it, or perhaps random turbulence causes a dense knot to form. Whatever the trigger, a region of the cloud starts contracting. As it shrinks, it breaks into clumps, each clump destined to form one or a few stars. Within one collapsing clump, gas falls inward, the core grows denser, and the temperature rises. What was once a diffuse, frigid region becomes a tight, hot pocket, the seed of a new star, called a protostar. At this stage, the protostar is not yet truly a star because nuclear fusion hasn't begun in its core. It's essentially a giant, warming ball of gas, growing by drawing in material from the surrounding cloud. It may be hidden within a cocoon of dust, opaque to our view. Over tens of thousands to millions of years, the protostar gains mass and heats further. It spins, and the infalling material often forms a rotating disk around it, the birthplace of potential planets to come. When the protostar's core temperature reaches around 10 million degrees Celsius, a transformation occurs. Hydrogen atoms begin to fuse together to form helium. This is the moment of ignition, the birth of a true star. Fusion unleashes a tremendous outpouring of energy. The protostar's core, once sustained purely by gravitational energy, becomes a nuclear furnace. With that, the young star blows away the remnants of its birthing cloud. The surrounding dust and gas are cleared by strong stellar winds and radiation, almost like a newborn pushing away its blanket. A star is born, shining by its own light, where before there was only a collapsing cloud. But a star's life isn't a single explosive event. It's a long, steady burn. After ignition, a star settles into a stable form. Here's the key to a star's existence: balance. The force of gravity is always trying to squeeze the star inward. The star's own mass pulls it toward collapse. But now, the core's fusion reactions produce an outward pressure from the extremely high temperature gas pushing outward. So, gravity pulls in, the core pressure pushes out, and at a certain size, these forces balance perfectly. The star stops contracting and finds an equilibrium size and brightness. It's like a cosmic tug of war that ends in a draw. The star neither collapses nor explodes, but holds itself together in a stable sphere. This state is called hydrostatic equilibrium, a fancy term for the balance of gravity and pressure. Without memorizing the term, we can appreciate the idea. The star is in a long-lasting peace, its internal forces in harmony. When a star reaches this balance, it enters the long adult phase of its life, known as the main sequence. In this phase, a star steadily fuses hydrogen into helium in its core, and as a result, gives off a consistent flow of energy. Our Sun is in this stage right now, and has been for about 4.6 billion years. Main sequence stars like the Sun will spend the majority of their lifetimes in this stable condition. In fact, most of the stars we see twinkling in the night sky are in this golden phase of life, quietly burning their nuclear fuel at a steady rate. A star on the main sequence can be thought of as middle-aged, maintaining a balance, shining at a roughly constant brightness for a very long time. Summing up, a star is born from gravity's relentless pull in dark clouds, ignites in a burst of fusion fire, and then lives out a very long life as a colossal, self-contained nuclear engine, held together by the graceful balance of gravity and pressure. From the outside, a star like our Sun appears steady, tranquil, even eternal in human eyes, rising and setting day after day. But inside, it's a raging inferno, an ocean of plasma with atoms colliding and fusing, releasing the energy that warms planets and lights skies. This inner drama is invisible to us, but it's the very reason stars shine. A star is, in truth, a cosmic flame that kindles itself out of the darkness of space and glows, sometimes for billions of years. Every star we see is a story of equilibrium, gravity trying to crush it, fusion pushing back, neither winning, the star shining on. Fusion, the heart of the Sun's fire. To grasp the Sun's power, we must peer into its core, a place of almost unfathomable heat and pressure, and witness the miracle of fusion. The Sun's core is about 15 million degrees Celsius. The plasma, hot, ionized gas, there is crushed by overlying layers to more than 100 times the density of water. Imagine an environment where every cubic centimeter of gas weighs more than a cubic centimeter of lead, and it's so hot that atoms are stripped into nuclei and electrons. In this environment, the normal rules that keep atomic nuclei apart, their positive charges make them repel each other, are overcome by sheer speed and closeness. Nuclei, protons, in the case of hydrogen, are moving so fast and are so tightly packed that they occasionally collide head-on despite their repulsion. When two hydrogen nuclei slam together with sufficient force, they can fuse into a single, heavier nucleus. This act releases energy. It's the fundamental reaction that powers the Sun. In our Sun, the main fusion process is a sequence called the proton-proton chain. In essence, 4 hydrogen nuclei, protons, ultimately combine to form one helium nucleus. The details involve a few intermediate steps and particles, but the key point is that the helium nucleus has slightly less mass than the 4 protons that went into it. That missing mass is not really missing. It's been turned into energy, as quantified by Einstein's E equals mc2. Even a tiny amount of mass yields an enormous amount of energy when converted. And the Sun converts mass to energy on a colossal scale. Around 600 million tons of hydrogen are fused into helium each second in the Sun's core. In the process, about 4 million tons of matter is converted into pure energy every second. Think about that. 4 million tons, the mass of a mountain, disappearing each second to light and heat. The sun has been doing this for billions of years and will continue for billions more. These numbers defy easy imagination. Let's try a comparison. If we could harness the sun's energy output for just 1 second, it would satisfy the entire energy needs of human civilization for hundreds of thousands of years. The sun's power output is about 4 times 10^26 watts. That's 4 followed by 26 zeros. It's equivalent to detonating billions of nuclear bombs each second. Yet it doesn't incinerate itself all at once because its mass is so immense, and the energy is released at a controlled rate governed by the balance we described. To visualize a single fusion event, in the sun's core, 2 protons, hydrogen nuclei, hurtle toward each other in the dense plasma. They collide and stick together. In that process, 1 proton transforms into a neutron, emitting a positron and a neutrino. The result is a deuterium nucleus, 1 proton plus 1 neutron. Soon, this deuterium nucleus collides with another proton, forming helium-3, 2 protons plus 1 neutron, and releasing energy. Finally, 2 helium-3 nuclei collide, rearrange into a helium-4 nucleus, 2 protons plus 2 neutrons, and spit out 2 excess protons. Those free protons can start the cycle again. Each step releases energy, carried by high-speed particles and photons, gamma rays. This chain reaction is happening trillions upon trillions of times per second in the sun's core. One remarkable byproduct is the neutrino, a nearly massless particle that hardly interacts with matter. Neutrinos generated in the sun's core zip straight through the sun and out into space at nearly the speed of light. Millions of them pass through your body every second, day or night, and you never notice. For a long time, neutrinos were the only direct evidence of what was happening in the core, since photons take much longer to reach us. In fact, detecting solar neutrinos in underground laboratories was a major success of late 20th century physics, confirming that fusion is indeed occurring as theory predicts, and revealing the quirky nature of neutrinos themselves. Fusion is a kind of alchemy, turning the simplest element, hydrogen, into helium, and in the process, releasing the energy that makes stars shine. It's nature's way of tapping the energy stored in matter. Our sun has been performing this trick for a very long time, and will continue for a long time to come. It has enough hydrogen in its core to keep fusing for roughly 10 billion years total, and it's not even halfway through that supply. So, when you look at the sun, you're seeing a giant ongoing thermonuclear reaction, not chaotic and explosive like a bomb, but a stable, self-regulating burn. It's a bomb that has been exploding for eons and will continue as a warm, steady glow. The fury in the sun's core is balanced and contained by gravity. From it comes all the warmth and light that bathes Earth and supports life. The next time you feel the sun's warmth on your skin, remember that it started as the furious collision of protons in a distant, dense, hot place, a place we'll never directly see, but which is the source of almost every experience of light or warmth we have ever known. From core to sky, the journey of light and heat. The energy produced in the sun's core does not emerge at the surface instantly. In fact, the journey from the sun's center to its surface is a long, tortuous odyssey for a newborn photon, particle of light. When a gamma-ray photon is first created by fusion in the core, it finds itself in an extremely dense environment. The sun's interior is effectively opaque. A photon can travel only a very short distance, less than a centimeter often, before it hits a particle, usually an electron or an atomic nucleus, and gets absorbed or scattered in a new direction. Imagine trying to escape a crowded room by blindly bouncing off people over and over. That's what a photon's path is like in the sun's interior. This process is often called a random walk. A photon takes a zigzag path, being absorbed and re-emitted countless times. And each time it's re-emitted, it might be of a slightly lower energy, since it can transfer energy to the matter. Thus, as energy travels outward from the core, the character of that energy changes. Gamma rays from the core gradually become X-rays, then ultraviolet, and by the time energy reaches the sun's visible surface, much of it is in the form of the visible light we are familiar with. But the key point is, this migration is slow. It can take a very long time. Estimates range from tens of thousands to hundreds of thousands of years, for energy from the sun's core to finally reach the surface as heat and light. In other words, the sunlight that reaches Earth today was generated in the sun's core long before human civilization began. It's been on a long journey within the sun, bouncing its way out. Now, about 70% of the way from the sun's center to its surface, so roughly 150,000 kilometers below the surface, the mode of energy transport changes. By this point, the temperature has dropped and the density is lower compared to the core, and the gas becomes more opaque to certain kinds of radiation. Photons find it harder to get through, so another process takes over: convection. If you've watched a pot of water boil, you've seen convection. Hot water rises, cool water sinks, forming a rolling boil of circulating fluid. Similarly, in the outer 30% or so of the sun, the convective zone, the energy moves by the motion of the gas itself. Hot plasma heated by radiation from below becomes buoyant and rises toward the surface, carrying energy upward. When it reaches the surface, the photosphere, it radiates its heat into space as the sunlight we see, and cools down, becoming denser and sinking back down to be reheated in a continuous cycle. This boiling motion of the sun's surface is actually visible with the right instruments. We call the pattern granulation. Seen through a solar telescope with appropriate filters, the sun's surface looks like it's covered in tiny cells or granules, each about 1,000 kilometers across, about the size of Texas or France. These granules are the tops of convection cells. The brighter center of each granule is where hot plasma is rising. The darker edges are where cooler plasma is descending. Each granule lasts on the order of minutes before dissipating and being replaced by a new one, as the boiling is continuously happening. So the sun's surface is not solid or static. It's a roiling, boiling sea of hot gas. Finally, the energy that started in the core, after its long random walk and its convective ride, reaches the photosphere, the layer of the sun from which light can escape freely into space. The photosphere is what we typically refer to as the surface of the sun, even though it's not a solid surface, just the visible layer of gas. It's only a few hundred kilometers thick. By now, the temperatures have dropped to about 5,500 degrees Celsius. From this layer, the photons are mostly free. They travel straight out into the solar system at the speed of light. Once the photons leave the sun, the rest of the journey is quick. They cover the 150 million kilometers to Earth in about 8 minutes and 20 seconds. Think about that contrast. Thousands of years to go from the core to the surface, but just minutes from the surface to Earth. The energy's hardest part was getting out of the sun. Crossing space is comparatively easy, since space is nearly empty and transparent. So, the sunlight that warms your face on a summer day was actually generated in the sun's core an age ago, spent eons fighting its way through dense plasma, and then zipped through space in a brief flash to arrive in that patch of sunlight you enjoy. It's humbling and a bit mind-bending that the sunshine we depend on has such a grand backstory. Born in a thermonuclear crucible, imprisoned in a maze of particles, carried upward by giant circulating currents, and finally released, only to travel across space and perhaps end its journey warming the wing of a butterfly or the face of a child. Every bit of sunlight has a tale to tell of the sun's interior life. We don't feel any of that when we bask in the sun. We just feel warmth and see light. But hidden in that gentle sunlight is the history of a photon's epic adventure. In a way, when you squint at sunlight, you're looking at a message from the sun's core, albeit a very old one. The spectrum of sunlight, visible and invisible. What we call sunlight is actually a medley of different kinds of light, only some of which our eyes can see. If you've ever admired a rainbow or watched sunlight split through a prism, you've seen that sunlight contains many colors: red, orange, yellow, green, blue, violet, the visible spectrum. These colors together make the sun's light appear white or golden to our eyes. Our sun is a remarkably broad spectrum light source. It shines in many wavelengths beyond just the visible band. Let's start with the visible part, since that's what we directly experience. The sun's surface temperature, 5,500 degrees Celsius, causes it to emit a lot of light around the middle of the visible spectrum, yellow-green light, but plenty in other colors too. Our eyes evolved to see the sun's most abundant wavelengths. That's no coincidence. Under sunlight, we perceive a world of colors because objects reflect some wavelengths and absorb others. A leaf looks green because it reflects green light to your eyes, while absorbing red and blue for photosynthesis. Snow looks white because it reflects almost all the sunlight's colors equally. Sunlight is the paint that colors our world. Beyond the visible lies the infrared, IR, on one side and the ultraviolet, UV, on the other. Infrared light has longer wavelengths than red light. We can't see IR, but we can feel it as heat. On a sunny day, much of the warmth you feel is from infrared radiation. In fact, roughly half of the solar energy reaching Earth's surface is in the infrared range. Ultraviolet light has shorter wavelengths than violet light. We can't see UV either, but some insects, like bees, can. UV is more energetic. It's what causes sunburn and can damage living tissue. Only about a few % of the sun's output is ultraviolet by energy, and thankfully, Earth's atmosphere filters a lot of that out, especially the high-energy UVC. If it didn't, life as we know it, certainly on land, probably couldn't exist without severe protection. The sun's spectrum actually goes even further. It emits some X-rays and gamma rays, very high-energy photons, primarily during solar flares or from the super-hot corona, though those don't reach the ground, blocked by our atmosphere, which is a good thing for us. It also emits radio waves on the long end of the spectrum, especially during solar storms or from plasma oscillations in the corona. So the sun produces everything from radio waves to gamma rays, but the bulk of its light is in the infrared, visible, and a bit of ultraviolet. Our atmosphere acts like a filter or sieve for this spectrum. It's transparent to visible light, hence we see the sun and daylight, mostly transparent to radio waves, so we can detect radio from space, partly transparent to infrared. Some IR gets through, some is absorbed by atmospheric gases like water vapor and CO2, and largely opaque to ultraviolet. The ozone layer gobbles up most UVC and UVB, sparing us from lethal doses, leaving just enough UVA and some UVB to cause tans and burns. This filtering is crucial for life. It lets in the nourishing parts of sunlight and keeps out much of the harmful high-energy radiation. Sunlight interacting with the atmosphere also creates beautiful effects. One famous effect is why the sky is blue. Sunlight is made of all colors, but as it travels through the atmosphere, the shorter wavelength light, blue, violet, scatters more off-air molecules than the longer wavelengths, red, orange. During the day, when the sun is high, this scattering sends blue light all across the sky, so no matter where you look, except directly at the sun, you see that scattered blue, hence a blue sky. Meanwhile, the direct sunlight coming to you from the sun has slightly less blue in it, since some was scattered away, giving the sun a mild yellow tinge when observed from Earth's surface. In space, the sun is actually white. At sunrise or sunset, the effect is more extreme. Sunlight has to pass through a thicker slice of atmosphere because it's coming in at a low angle. So much of the blue and green gets scattered out that the remaining sunlight that reaches your eyes is predominantly red and orange. Thus dawns and dusks glow in those warm hues. The scattered blue light at those times gets directed elsewhere, and when the sun is below the horizon, that scattered light can still make the sky glow long after sunset in twilight colors. Sunlight also contains hidden cues. For example, many flowers have patterns visible in UV that guide pollinators like bees, a sort of UV nectar guide on petals that we humans don't see without special cameras. Likewise, some birds have plumage with UV reflectivity, so they see each other more ornately than we see them. Snakes that hunt warm-blooded prey at night can see in infrared using special organs, effectively sensing the heat signature of a mouse in the dark, essentially perceiving the IR part of that mouse re-radiating stored solar energy, food energy that mouse got ultimately from plants and sun. Thus, the sun's spectrum influences life and perception in diverse ways. Plants use visible light, mostly red and blue, for photosynthesis. They don't use much green, which is why they reflect it and appear green. The ozone layer's creation by early photosynthetic life then shielded the land from UV, enabling life to emerge from the oceans and evolve on land. Our own circadian rhythms are tied to the cycle of solar light, particularly the blue part of the spectrum, which signals morning to our brains. We have technology to detect all these wavelengths. Radio telescopes listen to the sun's radio output. Satellites like SOHO or SDO watch the sun in ultraviolet and X-rays, revealing activity that's invisible to us from Earth's surface. All told, sunlight is a rich broth of electromagnetic radiation. We experience it as a gentle warmth and a bright light, but within that brightness is a rainbow of colors and an invisible symphony of other wavelengths. Each has its effect. Infrared warming surfaces, visible light enabling vision and powering photosynthesis, ultraviolet sparking chemical changes, like vitamin D production in our skin, or sometimes sunburn. Our sun gives us not just light, but a spectrum, the full palette needed to paint life on Earth. The solar cycle, the sun's 11-year heartbeat. On human timescales, the sun seems unwavering. It rises and sets daily. The daylight feels more or less constant aside from clouds and seasons. But the sun is not perfectly constant. It has its own cycles and rhythms. The most notable is the approximately 11-year solar cycle of magnetic activity, often likened to a heartbeat or the sun's breathing. This cycle is most visibly reflected in the number of sunspots on the sun's surface. Sunspots are dark, relatively cool patches on the photosphere. They look dark only by contrast, because they are a few thousand degrees cooler than the surrounding surface, so they emit less light. A sunspot might be 4,000 degrees Celsius instead of 5,500 degrees Celsius around it. Still very hot and bright, but dimmer than its environment, so it appears dark to us. Sunspots can be enormous, some larger than Earth in diameter. Importantly, sunspots are regions of intense magnetic activity. You can think of them as storm systems in the sun's magnetic field. They often come in north-south polarity pairs, connected by loops of magnetic field arching above the surface. At the start of a solar cycle, called solar minimum, sunspots are few, sometimes none at all. The sun's face can be blank for days at a time. As the cycle progresses, sunspots appear, initially at mid-latitudes on the sun. If we imagine the sun's equator, spots first pop up around 30 degrees north and south. Over a few years, we get more and more sunspots. That's the rise towards solar maximum. Sunspots also tend to form closer to the equator as the cycle goes on. At solar maximum, the sun's disk might be freckled with spots. Dozens can appear at once, and big ones spawn little ones. Then after the peak, the number of spots begins to decline. By the time of the next solar minimum, the sun is quiet again. Then a new cycle starts, with spots reappearing. But interestingly, the magnetic polarity of the spots flips. The sun's magnetic field does a flip every cycle. So really, it's a 22-year magnetic cycle, with a polarity flip every 11 years. What's behind this cycle? It's the sun's magnetic dynamo at work. The sun is a huge sphere of conducting plasma that rotates and has convection. Those are ingredients for generating magnetic fields. Furthermore, the sun's equator rotates faster than its poles, a 25-day rotation at the equator versus about 35-day at the poles. This differential rotation winds up and tangles the solar magnetic field lines over time. Imagine stretching and twisting a rubber band. Eventually it might snap or reconfigure. The leading explanation, simplified, is that as the field gets twisted, magnetic loops buoyantly rise through the sun's surface. Those spots where they emerge are sunspots, where the field bursts out, suppressing the hot rising plasma and thus cooling the area slightly. Over the cycle, more tangles mean more spots and more activity. Eventually, the field gets so twisted, it essentially reorders itself, flipping the polarity and simplifying, leading to fewer spots, and the cycle starts anew with reversed magnetic orientation. We observe these cycles by counting sunspots, historically the way since the 1700s, and now by measuring the sun's magnetic field directly and its various emissions. Some cycles are stronger, lots of sunspots, very active. Some weaker. The period can also vary a bit. Not every cycle is exactly 11.0 years. Some are 9, some 13, etc. Beyond sunspots, the solar cycle affects other solar phenomena. During solar maximum, the sun often unleashes more solar flares, sudden bursts of X-rays and energy, and coronal mass ejections, CMEs, huge blobs of plasma thrown into space. These typically erupt from magnetically active regions around sunspots. The sun's entire plasma environment is rowdier, the corona has more disturbances, the solar wind is more irregular. At solar minimum, flares are few. CMEs happen less often, and the sun's atmosphere is calmer. This cycling has effects on Earth and our technological systems, which we'll talk more about in the space weather section. But even before modern technology, nature gave hints. For instance, the auroras, northern and southern lights, become more frequent and intense around solar maxima because they are triggered by solar activity interacting with Earth's magnetic field. Historically, there have been notable deviations. The Maunder minimum, 1645 to 1715, was a period during which sunspots almost disappeared for 70 years. The sun still had an 11-year cycle, we think, but it was extremely weak. This coincided with the coldest part of the Little Ice Age, suggesting maybe a small impact on Earth's climate. The sun's output might have been slightly lower. On the other hand, the late 20th century had some of the most active cycles on record. The sun was a bit brighter and more active, though again, not dramatically so. We're now aware that while the solar cycle modulates the sun's emissions a little, it doesn't change enough to cause big climate changes. The difference in total energy between solar max and min is on the order of 0.1%. Still, for scientists trying to understand climate, it's an important factor to account for when looking at natural variability. From a human perspective, the sun's cycles remind us that it is a dynamic star, not a static light bulb. If you could speed up time, you'd see the sun's face constantly changing, spotted, then clear, then spotted again, like it's breathing in and out on a decade scale. We often call it the sun's heartbeat. Living through one cycle, say 11 years, we might notice little differences, maybe slightly more auroras or shortwave radio interference around the active years. But overall, life goes on normally, which is fortunate. It's a testament to the sun's stability that these cycles don't drastically affect our daily lives beyond some subtle phenomena. However, for astronauts in space, or engineers of satellites and power grids, knowing where the sun is in its cycle is important. During solar max, the chance of a big solar flare, or CME, that could disrupt communications or electronics is higher. Thus, scientists at agencies like NASA and NOAA carefully monitor the sun's activity and make predictions about the solar cycle. The solar cycle is also an object of scientific fascination because it's a window into the sun's magnetic soul. Even after centuries of observation, We don't fully understand all the details of what causes it and modulates its intensity. It's one thing to notice the pattern. It's another to predict, for example, how strong the next solar cycle will be. Sometimes predictions are off. The cycle surprises us. So, it's an active area of research in solar physics. In sum, the Sun has an internal rhythm of approximately 11 years, swinging between times of relative calm and times of heightened activity. It's like the Sun's own seasons. We're fortunate that even stormy for the Sun is still gentle enough to allow life to flourish on Earth. The Sun's variability is small compared to its overall output, but those variations are significant enough to study and track. It's amazing to think that deep inside the Sun, magnetic fields are twisting and flipping on that timetable, and the effects echo all the way out to Earth and the planets. The Sun's heartbeat is the pulse of the solar system, and we're just starting to truly listen to it. Space weather, solar storms, and Earth's response. The Sun doesn't just shine, it also blows. It continuously emits a stream of charged particles called the solar wind, a flow of plasma, mostly electrons and protons, that races out in all directions, filling the solar system. And at times, the Sun storms. It releases bursts of particles and energy far more intense than the normal solar wind. Collectively, the variable conditions in space caused by the Sun and their effects on planets are known as space weather. On a quiet day, the solar wind is like a gentle breeze. It takes a few days for solar wind particles to go from Sun to Earth. This wind shapes and distorts Earth's magnetic field into a windsock-like shape, the magnetosphere. Most solar wind particles slide around this magnetic bubble, sparing us from their direct impact. But the Sun can fire off big blasts that dramatically disturb Earth's magnetic environment. One form of solar storm is the solar flare, essentially a massive explosion on the Sun's surface, actually in the lower atmosphere corona, that releases a flood of electromagnetic radiation from radio waves to X-rays and accelerates particles to high speeds. If the Earth is line of sight to the flare, we can get a surge of X-rays and extreme UV within minutes, since those travel at light speed. Another, often more disruptive type of event is a coronal mass ejection, CME. That's when a huge blob of the Sun's corona, containing billions of tons of plasma, is thrown into space at high speed. Imagine an immense magnetic bubble filled with charged particles, ejected like a cannonball. If that CME is aimed at Earth, we have a few tens of hours, typically 1 to 3 days, before it arrives. When it does, it slams into Earth's magnetic field. What happens next is a geomagnetic storm. Earth's magnetic field, normally a fairly stable protective cocoon, gets buffeted and perturbed by the shock of the CME and the injection of charged particles. The magnetic field lines stretch, twist, and reconnect. Particles from the Sun are funneled along Earth's magnetic field into the upper atmosphere, especially near the poles, because Earth's field lines intersect the atmosphere near the north and south magnetic poles. These high-energy particles collide with atoms and molecules in our atmosphere, mostly oxygen and nitrogen. When those atmospheric atoms get excited and then return to their normal state, they emit light, producing the glowing curtains of the auroras, Aurora borealis in the northern hemisphere, Aurora australis in the southern. During a strong solar storm, auroras that are normally confined to polar regions can descend to lower latitudes. There are historical accounts of auroras being seen near the equator during the most extreme storms. But auroras, while beautiful, are the benign side of space weather. The same geomagnetic disturbances can induce electrical currents in long conductors on the ground, like power lines and pipelines. In extreme cases, these currents can overload power grids. For example, in March 1989, a strong geomagnetic storm triggered by a CME caused a major power blackout in Quebec, Canada. The induced currents took down transformers, and the grid went offline for hours. That was a wake-up call that a solar tantrum can affect modern infrastructure. Another effect is on satellites and spacecraft. When the sun is stormy, satellites can experience surges of charged particles that cause electrical charging and discharging, sparks essentially, on their components, which can damage electronics. Satellite operators will sometimes put spacecraft in a sort of safe mode during major solar storms to protect them. High-frequency radio communication, used by aircraft, ships, ham radio operators, can be disrupted when solar flares increase ionization in Earth's upper atmosphere, the ionosphere, causing radio signals to fade or behave unpredictably. GPS signals can also become less accurate due to ionospheric disturbances during solar storms. Astronauts, especially those outside Earth's protective magnetosphere, like future Moon or Mars travelers, have to worry about solar particle events, bursts of energetic protons from flares, or shock fronts of CMEs. These can deliver significant radiation doses. On Earth, we're mostly shielded by the combination of our magnetic field and atmosphere. At most, high-altitude flights near the poles during a big solar event might give slightly elevated radiation exposure to passengers and crew. Not usually dangerous, but measurable. The most intense solar storm on record is often cited as the Carrington event of 1859. It caused telegraph systems, the cutting-edge tech of the time, to spark and catch fire, and brilliant auroras worldwide. If a Carrington-class event hit Earth today, it could be quite damaging to our technological infrastructure, potentially frying satellites, knocking out a lot of transformers on power grids, and disrupting communications globally. It's something scientists and emergency planners think about quite a bit. Such extreme events are rare, but not impossible, perhaps a few per century. This is why there's a whole field of space weather forecasting. We have satellites like NASA's ACE and DSCO-VR stationed 1 million miles sunward from Earth that act as an early warning station, detecting incoming solar wind changes about an hour before they reach Earth. We have the Solar Dynamics Observatory, SDO, and SOHO, watching the sun for flares and CMEs, and numerous other spacecraft like Parker Solar Probe, Solar Orbiter, Stereo, etc., studying the sun and heliosphere. When a big flare or CME is detected, alerts go out to power grid operators, satellite companies, airlines, etc., so they can take precautions, adjust satellite orbits, have planes avoid high latitudes, etc. in extreme cases. Living with a star means occasionally feeling its wrath, but it's also because of our star that life can exist at all. Space weather is the price we pay for having an active, life-giving sun. In fact, some solar scientists make an interesting point. A more active sun in its youth, with more frequent flares, might have helped spark the chemistry of life on the early Earth by providing energy and creating useful molecules via radiation. And the auroras and subtle climate nudges aside, the sun's variability likely hasn't been bad for us historically. Not until we built a technologically delicate society in the past century did solar storms become a concern. So, space weather is about understanding the Sun-Earth connection in real time. It's the modern counterpart to ancient people noticing that the sun can, on rare occasion, do strange things, like the skies glowing or the sun having spots. We've gone from interpreting those as omens to measuring them with instruments and integrating them into our technological planning. The takeaway: the sun has a calm side, sunshine, and a stormy side. The stormy side manifests in solar flares and CMEs that can shake Earth's magnetic field and excite our sky with auroras, and, in our wired world, even induce currents in our systems. Each event ties us a little more to our star. It reminds us that we're riding through space inside the sun's atmosphere effectively. We have not just weather on Earth, but weather in space, and our star is the driver of it. Sunlight and life, the sun's gift to Earth. Take away the sun, and Earth would be a frozen, lifeless rock. With the sun, our planet thrives with oceans, forests, and living creatures. The sun's role in sustaining life on Earth cannot be overstated. It is the primary source of energy for almost every process that makes our world habitable. In a very real sense, sunlight is life. Consider the foundation of the food chain: photosynthesis. Green plants, algae, and certain bacteria capture sunlight and use its energy to turn carbon dioxide and water into sugars, food, and oxygen. They literally eat sunlight and exhale the oxygen we breathe. In doing so, they create food not just for themselves, but for all other creatures. The grass a cow munches, the wheat that becomes our bread, the fruits we pluck from a tree, all are products of sunlight transformed by life. When you eat an apple, you're eating stored sunshine that the apple tree drew in. Even the oxygen in every breath is largely a gift of photosynthesis powered by the sun. Over billions of years, tiny organisms and later plants filled our atmosphere with oxygen by harvesting solar energy. Every breath you take is a quiet gift from the sun via the living world it sustains. The energy flow doesn't stop there. Herbivores eat the sun-fed plants. Carnivores eat the herbivores. Decomposers break everything down and return nutrients to the soil, but even they live on the energy originally captured by plants. The entire teeming biosphere, from deep-sea plankton to rainforest trees to humans, ultimately runs on solar power. There are a few exceptions. Ecosystems around deep ocean hydrothermal vents derive energy from Earth's interior heat and chemicals, not the sun. But those are rare pockets. The vast majority of life on Earth, especially on the surface, is utterly dependent on sunlight. If the sun's light flickered out, photosynthesis would halt within days. Plants would die, oxygen would dwindle, food chains would collapse. Earth's temperature would plummet. Complex life would soon perish. Thankfully, the sun is steady on human timescales, rising each day and powering the cycles of life. Beyond feeding life, the sun shapes our environment in countless ways. Take the water cycle. The sun's warmth evaporates water from oceans, lakes, and soils, lifting it as vapor into the air. That vapor cools to form clouds, which eventually rain or snow, replenishing water to the land. Without the sun, there'd be no evaporation, no rain. The Earth's great irrigation system would shut down. Every raindrop and snowflake owes its existence to solar heating. The sun also drives our weather and climate. The uneven heating of Earth, equator getting more direct sun than poles, land heating differently than ocean, etc., sets the atmosphere in motion. Warm air expands and rises in the tropics. Cooler air sinks near the poles, and winds form to redistribute heat. The gentle breeze at the beach blowing from sea to land during the day, that's because the sun heats the land faster than the water, making air rise over land and drawing cooler air from over the water. A mighty hurricane. It's powered by the sun-warmed ocean giving energy to the air. Patterns like monsoons, trade winds, jet streams, ultimately shaped by how the sun's energy flows through the Earth system. Climate itself, the long-term patterns of temperature and rainfall, are anchored by how and where the sun's heat is delivered, though factors like ocean currents and atmospheric composition play a big role too. The difference between a tropical rainforest and a polar ice cap environment is largely one of solar energy received. Consider seasons. Why do we have spring, summer, autumn, winter in many places? Because Earth's axis is tilted relative to its orbit around the sun. As we orbit the sun each year, the tilt causes each hemisphere to get more sunlight for half the year and less for the other half. The sun rides high in the sky in summer, delivering more intense, longer-lasting light, and low in winter, giving weaker, shorter light. That's why summer is warm and winter is cold. This solar-driven cycle has shaped how organisms behave. Trees shed leaves when sunlight wanes, animals hibernate or migrate, and humans, historically, timed crops and festivals to the solar calendar. Many cultures have solar New Year celebrations around the winter solstice, when the sun's daily path starts to lengthen again, signaling hope of returning warmth. The sun's light even orchestrates daily biological rhythms, the circadian cycles of most living things. The alternation of day and night sets an internal clock in organisms, affecting sleep, feeding, hormone production, and more. We are creatures that evolved under a stable 24-hour light-dark cycle from the sun, and our bodies still reflect that, even if electric lighting has extended our day artificially. Beyond direct energy, the sun's influence likely shaped Earth's very atmosphere and climate over geological timescales. For example, the young sun was dimmer, yet Earth was not a snowball, possibly because greenhouse gases were higher, as mentioned, compensating for the fainter sun. Over billions of years, as the sun brightens slowly, Earth's life and geology have worked in tandem to keep the climate within bounds conducive to life, through processes like CO2 regulation via rock weathering, etc. This incredible long-term balance, sometimes called the Gaia hypothesis in spirit, is essentially life adjusting the planetary thermostat in step with the sun's output. We should also mention that nearly all fossil fuels, coal, oil, natural gas, are essentially ancient sunlight. They are the remains of plants and plankton that lived millions of years ago, capturing sunlight, and then were buried and transformed by geological processes. When we burn them, we're releasing that stored solar energy. Even things like wind power and hydropower are indirect solar gifts. Wind is driven by solar heating differences. Hydropower uses water elevated by the solar-driven water cycle. Solar panels, of course, directly convert sunlight to electricity. In essence, almost every energy source we have, save nuclear and geothermal, is solar in origin. The sun's role in sustaining life also makes it central to many cultural narratives. Nearly every ancient civilization had a sun deity or some form of sun worship, a recognition that the sun was the bringer of life. From the Egyptian Ra to the Inca Inti to ceremonies like sun dances and solstice observances, human culture has long paid respect to the sun's life-giving role. Even today, we speak of a sunny disposition as a metaphor for happiness and find sunny days more uplifting. Even as we harness atomic energy or dream of fusion reactors, we're just trying to replicate on a small scale what the sun does naturally. It remains the main engine that drives Earth's systems. The sun evaporates our waters, stirs our winds, grows our food, and fuels our spirits. On the flip side, the sun also has the power to harm life. Too much sunlight can cause droughts, deserts, sunburn, or skin cancer. It's a reminder that while we depend on the sun, we also need to respect it. But overall, Earth sits in a Goldilocks zone around the sun, where we usually get just the right amount of energy. In summary, the sun sustains life by providing energy for photosynthesis, which feeds ecosystems and produces oxygen, driving the water cycle, ensuring fresh water and rainfall, powering winds and weather, distributing heat and moisture, maintaining climates and seasons, to which life has adapted in myriad ways, setting timekeepers, day-night, yearly cycles, that life has evolved to anticipate and use, and generally keeping Earth warm enough for liquid water. When you see a thriving green forest, a bustling city, or a coral reef teeming with fish, remember that it's all running on solar power. Life is a planetary-scale project of turning sunlight into living structure and motion. In a poetic sense, if you look at a tree, or even your own body, you could say, this is what sunlight can do when given time and the machinery of life. It becomes wood, leaf, muscle, bone, thought. The sun doesn't just shine on us, it lives through us in a way, as the energy that animates Earth's biosphere. Aging star, inevitable demise, how the sun will end and take Earth with it. The sun feels eternal and unchanging in our lives, but like all stars, it has a finite lifespan. It is middle-aged now, about 4.6 billion years old, And over the coming eons, it will undergo profound changes. In the very distant future, those changes will dramatically alter the solar system and likely spell the end of life on Earth. The story of the sun's aging is both majestic and sobering, a tale of transformation that will turn our gentle sun into a much more hostile entity for a time, before it finally fades. Right now, the sun is in a long stable phase, fusing hydrogen into helium in its core. However, even during this stable phase, subtle changes are happening. As the core gradually accumulates helium ash from fusion, it very slowly contracts and heats up, because helium doesn't fuse at the current temperature, so the core's energy output must come from a contracting core and hydrogen fusing in a shell around it. This makes the sun's nuclear reactions a bit more efficient over time. In fact, over the past 4.5 billion years, the sun's luminosity has increased by roughly 30%, and it will continue to brighten about 1% every 100 million years or so. That sounds small, but in a billion years, 10% more luminosity might be enough to significantly change Earth's climate. Climate models suggest that within about 1 to 1.5 billion years from now, the sun's increased radiation could push Earth into a runaway greenhouse effect. Basically, more heat means more water evaporation. Water vapor is a greenhouse gas, which traps more heat, which causes even more evaporation, a vicious cycle. The oceans might slowly evaporate into the atmosphere. Temperatures would soar. By roughly a billion or so years from now, give or take, Earth could become a sweltering, lifeless, for complex life, planet, perhaps resembling a bit of a steam bath like a very hot Venus. Microbes might hang on in niche environments, but advanced life would be in big trouble. So, long before the sun dies, it will likely make Earth uninhabitable by our standards. But let's look further ahead. In about 5 billion years, the sun will run low on the hydrogen in its core. Fusion in the core will begin to falter. Without that outward pressure from fusion, the core will start to collapse under its own gravity. And when a gas compresses, it heats up. So the sun's core will get even hotter, even as it's filled mostly with helium now, since hydrogen was used up. This hotter core ignites hydrogen in a shell around the core, hydrogen that's in a layer that wasn't hot enough to fuse before. That fusion in the shell dumps energy into the sun's outer layers, pushing them outward. The sun's envelope, all the outer layers beyond the helium core, will expand tremendously. The sun will swell into a red giant. In the red giant phase, the sun will grow in size hugely, perhaps 100 times its current diameter or more. It's often said it could expand out to Earth's orbit or beyond. Current calculations suggest the sun's radius will indeed approach roughly Earth's orbit, maybe slightly less, maybe more depending on mass loss uncertainties. Mercury and Venus will almost certainly be engulfed. Earth's fate is a bit on the knife's edge. Some predict it will be swallowed as well, or if not swallowed, it will be extremely close to the sun's surface, basically grazing the giant star. In any case, whether Earth ends up inside the sun or just right next to it, it will be sterilized and possibly melted. Long before that happens, however, life would have been cooked away by the increasing heat. While the sun's radius balloons, its surface temperature will drop. The energy is spread over a much larger area, so its color will become more orange-red. But its total luminosity will actually increase enormously due to its vast size. In the red giant phase, the sun could be several thousand times more luminous than it is now. The sky for any surviving worlds far out, maybe moons of Jupiter or Saturn, would feature a huge red star where the sun once was, filling a good portion of the sky. Inside the red giant sun, the core, now mostly helium, keeps contracting and heating. Eventually, it reaches about 100 million degrees, hot enough for a new kind of fusion, helium fusion. In a sudden onset called the helium flash, for stars like the sun, the core ignites helium, converting it into carbon and oxygen. The sun, after a bit of a convulsion, stabilizes again for a while, now fusing helium in its core. It shrinks from its maximum red giant size and its surface gets hotter again, moving from a very cool red giant to a somewhat smaller yellowish giant. This stable helium-fusing phase won't last nearly as long as the hydrogen-fusing main sequence did, perhaps only on the order of 100 million years. During this time, the Sun will be a horizontal branch star, in astro jargon, or a clump star, not as large as the red giant tip, but still large compared to now, and still hundreds of times more luminous than today's Sun. But eventually, the Sun will exhaust the helium in the core too. Now it has a core of carbon and oxygen, products of helium fusion, and it lacks the mass to ignite those. The Sun won't reach the temperatures needed to fuse carbon, so fusion will stop in the core again, and the core will contract yet again. Shells of fusion, hydrogen and helium shells around the core, will ignite and cause the star to bloat into a second red giant phase, even larger perhaps, an asymptotic giant branch star. This is an extremely luminous and somewhat unstable period. The Sun will likely pulsate and lose a lot of mass through a strong stellar wind. In those final throes, over perhaps tens of millions of years, the Sun will shed its outer layers. Each pulsation or thermal pulse can blow off a shell of gas. These layers drift away into space. What will remain at the center is the hot core, carbon-oxygen, which will be exposed as the envelope is lost. When the hot core's intense ultraviolet radiation bathes the expanding gas shells, they will glow. This vision is called a planetary nebula, a bit of a misnomer historically, since it has nothing to do with planets. But through early telescopes, these objects looked like round, planet-like nebulous disks. The Sun will create a beautiful planetary nebula, perhaps a ring or bubble of multicolored gas, expanding outward over tens of thousands of years, then slowly fading as it disperses into the interstellar medium. At the heart of the planetary nebula will be the Sun's core remnant, a white dwarf. This will be an incredibly dense, Earth-sized object containing about half the Sun's mass. The other half was lost in the nebula. Its surface temperature initially will be very high, 100,000 K or more, so it will shine brightly in UV and blue light. But its small size means it has relatively low luminosity compared to a star. No fusion happens in a white dwarf. It's supported from further collapse by quantum mechanical pressure of electrons, electron degeneracy pressure. Over billions of years, it will cool and fade, eventually becoming a cold, dark black dwarf. Though the universe isn't old enough for any to exist yet, even the oldest white dwarfs are still warm. So, the sequence in summary: the Sun will go from main sequence, now, to red giant, swallow inner planets, to helium-burning giant, to shedding its layers to end as a white dwarf with a planetary nebula slowly dissipating around it. During the red giant phase, as mentioned, Earth's prospects are grim. Either it's swallowed or so close to the Sun's atmosphere that it superheats. There's speculation that as the Sun loses mass, Earth's orbit might expand, because less gravity means the planets drift outward a bit. But this likely won't save Earth from being crisped, and tidal interactions with the Sun's extended envelope might drag it inward anyway. Mars and the outer planets will move farther out due to mass loss of the Sun, so Mars might end up roughly where Earth's orbit is now, but by then the Sun's habitable zone will also have moved out. Though temporarily during certain phases, the habitable zone might sweep outward, possibly making moons of Jupiter or Saturn comparatively balmy for a short period. Interesting to imagine if distant future life or human settlers move there for a while. However, the habitable zone concept at that point is tricky because the Sun's evolution is rapid. The red giant phase isn't stable or long enough for life to do much adapting. It's likely that unless some far future technology intervenes, like moving planets, life in the solar system will either die out or perhaps survive only around the fringes, maybe in subsurface oceans of outer moons, during the Sun's giant phases. After the planetary nebula fades, the Sun's remnant white dwarf will linger for trillions of years, slowly cooling. The solar system by then will be a very different place. The inner planets will be gone or barren. The gas giants might remain, albeit colder and further out. Perhaps some will have surviving moons, but there will be no sunlight in the traditional sense, just a white-hot point gradually cooling to red, then infrared, then dark. It'll be a peaceful coda to a star that once shone brilliantly. It's quite poetic. The sun, which nurtured life, will eventually become a glowing ember, surrounded by the ghostly shell of its former self. That nebula will mix with the interstellar gas, and somewhere, far in the future, some of those atoms, our sun's carbon, oxygen, nitrogen, that came from Earth's atmosphere maybe, etc., might be incorporated into a new nebula that forms new stars and planets. The carbon in your DNA might one day be part of an alien apple on an alien world, orbiting a star that hasn't been born yet. In this way, the sun's death will sow the elements for new beginnings. For humanity, if we're thinking unimaginably far ahead, the lesson is clear. The Earth won't remain habitable forever. We have a very long but finite window, on the order of 1 billion years of decent habitability left, and maybe another few billion until Earth is completely toast. That's plenty of time to evolve, migrate, or innovate if any descendants of life, including possibly humans or our engineered progeny, are still around. The final chapters of the Earth will be written by the slowly changing sun. So the sun's demise is both a distant catastrophe and a cosmic recycling event. It's the end of one stellar life and potentially the seeds for many new ones. It's a dramatic reminder that even stars are not eternal. They have life cycles. Our sun is just special to us because we are part of its story. And hopefully, by understanding this story, we can appreciate our place in time, living in the warm spring of a star that will one day grow old and fade, as all things in the universe eventually do. Mysteries of the sun, puzzles of the corona and magnetic magic. One might think that by now, in the 21st century, we understand the sun completely. We have studied it for centuries and even sent probes to observe it up close. Yet the sun still guards some intriguing mysteries. The more we learn, the more questions arise in some areas. Two big unsolved or partially solved puzzles are particularly famous. Why the sun's corona, outer atmosphere, is so unexpectedly hot, and the complex behavior of the sun's magnetic field, including odd phenomena like magnetic switchbacks and the workings of the solar dynamo deep inside. First, the coronal heating problem. If you move away from a campfire, the air gets cooler. Naively, one would think as you move outward from the sun's core, the heat source, things should get cooler, and they do until a point. The sun's surface, photosphere, is about 5,500 degrees, but further out, in the tenuous corona, the temperature soars to over 1 million degrees Celsius, and in some regions during flares, tens of millions of degrees. This is counterintuitive. The air around the sun is far hotter than the surface itself. It's as if you walked away from a stove and the air 10 feet away was hotter than the stove's surface. Why is the corona so hot? This mystery has persisted for decades. The current thinking is that the sun's magnetic field is the agent delivering energy to the corona. There are two leading ideas, which may both be true to some extent: wave heating and nanoflares. Wave heating. The idea is that convective motions at the sun's surface shake the magnetic field lines. Like plucking a guitar string, sending waves upward. These could be Alfvén waves, magnetohydrodynamic waves, that travel through the corona. As these waves propagate, under certain conditions, they can dampen and dump their energy, heating the plasma. Nanoflares, proposed by astrophysicist Eugene Parker, namesake of the Parker Solar Probe. Nanoflares are like tiny, frequent versions of solar flares, too small to detect individually, but occurring all over the corona like popcorn. Each one releases a burst of heat. In aggregate, millions of nanoflares could heat the corona. Both mechanisms might be at work. So far, Evidence has been found for both waves and small flares. Parker Solar Probe, which is venturing into the Sun's corona itself, has detected abundant alphenic fluctuations in the solar wind, some possibly rooted in coronal processes, and strange magnetic switchbacks, sudden reversals in the magnetic field direction. Initially, it was thought these switchbacks might be signatures of energy release that could heat the corona, but more recent data suggests they originate lower down and maybe not in the corona itself. Solar Orbiter has seen tiny brightenings, campfires, which could be nanoflares. It remains an active area of research. It's a bit humbling that we still can't fully explain something as fundamental as how the Sun's outer atmosphere works, but we're getting closer with new data. Perhaps in the next decade, we'll have a consensus on the dominant heating mechanism. Another mystery, or set of mysteries, involves the Sun's magnetic field and internal dynamics. The solar dynamo, how exactly the Sun generates its 11-year magnetic cycle and all the magnetic complexity, is not completely understood. We have models, of course, but the Sun sometimes throws curveballs like irregular cycle timings or the Maunder minimum type events. There's also the question of why the Sun's polar magnetic field and deep interior processes produce the cycles they do. Solar Orbiter's upcoming high-latitude observations might shed light on that. Then there's the phenomenon of magnetic reconnection, which is understood in theory. It's when magnetic field lines break and reconnect, releasing energy, but predicting when and where it will happen, like what triggers a particular solar flare, is tricky. We can often see an active region is ripe to produce a flare, but exactly when a big one goes off is still hard to pinpoint. It's like forecasting an earthquake. The solar neutrino problem was a famous mystery. Back in the mid-late 20th century, early experiments detected only about 1/3 of the neutrinos predicted to come from the Sun's fusion. That was resolved not by changing solar theory, but by discovering that neutrinos oscillate change type en route to Earth. Thus, the detectors, sensitive only to one type, missed them. A victory for new particle physics, and confirmation that fusion theory was correct. Another intriguing area, the solar interior rotation. Helioseismology, studying sound waves that travel through the Sun, revealed that the Sun's radiative interior, inner 70%, rotates like a solid body, while the outer convective zone has differential rotation, fast equator, slower poles. The boundary between these, the tachocline, is thought to be crucial to the dynamo, but details of how exactly the flow and field in that region interact are still being researched, often through sophisticated computer simulations and more helioseismic data. We also have the question of the solar wind acceleration, how exactly the corona transitions into the supersonic solar wind. Observations show the solar wind accelerates rapidly within a few solar radii of the surface. Alphen waves may play a role in pushing it, and Parker Solar Probe is basically going there to observe that acceleration region directly. The switchbacks I mentioned are a new puzzle from Parker data. These are rapid flips in the magnetic field direction detected in the solar wind near the Sun. They indicate S-shaped kinks in the magnetic field. Initially, some thought they might be signatures of how the solar wind is being energized at the base, maybe by jets that produce kinks. Parker's findings that they persist and maybe originate below the Alphen point, inside the corona, suggests something interesting is happening in the low corona or upper chromosphere to create them. One idea is they could be generated by the deformation of magnetic field lines as they emerge from the coronal holes, open field regions. It's an ongoing investigation. Another domain of mystery. The Sun's corona produces high-energy particles, like during flares, or even continuously, giving cosmic rays an anomalous component. The details of how solar energetic particles are accelerated to near-light speeds by shock waves or reconnecting fields is an area overlapping with plasma physics and has implications for space weather predictions. We want to predict radiation storms for astronaut safety. While we've solved many solar riddles, we know it's fusion-powered, We know why sunspots are dark. We identified the solar cycle. We measured the composition, etc. The sun still surprises us. The fact that just in 2020, the Parker probe discovered phenomena we hadn't anticipated, like how prevalent switchbacks are, or the exact dust-free zone near the sun, shows that exploration is still yielding new insights. The sun is also our nearest laboratory for astrophysics. What we learn here, we apply to other stars. Conversely, observing other stars can inform solar theory. For instance, observing younger sun-like stars tells us that the young sun likely was more magnetically active, more flares, sunspots, wind, which has implications for early Earth and atmosphere evolution. Observing stars that are analogues of what the sun will be, red giants, white dwarfs, connects to our story of solar evolution. And some mysteries are more philosophical. What will the sun's variability be in the future? Are we sure it won't surprise us with another Maunder minimum? Or, opposite, a hyperactive cycle? Given that life and civilization are affected by even small changes, understanding and perhaps one day predicting the sun's long-term changes is of interest. Though right now climate change from human activity is a far bigger factor than any solar trend. It's quite fascinating that the sun, a seemingly simple object, just a big ball of plasma, exhibits such complex behavior that we still haven't unraveled everything. Plasma, ionized gas with magnetic fields, is inherently capable of very complex, chaotic behavior. The sun is basically a big plasma physics experiment that we can't fully replicate on Earth. Our fusion experiments are tiny and short-lived in comparison. The ongoing missions, Parker Solar Probe and Solar Orbiter especially, are sort of like sending microscopes to study the sun's workings up close. In the next few years, Parker will go even closer, within about 3.8 million miles of the sun's surface, which is within the corona, closer than Mercury's orbit. It might directly measure the microphysics of coronal heating or solar wind acceleration. Solar Orbiter will image the sun's poles, giving us a better handle on the magnetic field at high latitudes, critical for understanding the global dynamo. So the mysteries are gradually yielding. But as with all science, solving one often leads to the next deeper question. The sun has been at the center of scientific inquiry since Galileo's time, and even before, if you count ancient observations. It has taught us about gravity via planetary orbits, about light, prisms and spectra, about nuclear physics, fusion, about plasma physics, flares, coronal heating, and it continues to be a source of discovery. In learning about the sun's mysteries, we also indirectly learn about phenomena elsewhere in the cosmos, since the sun is a convenient test case for general astrophysical processes. For example, understanding magnetic heating in the sun's corona can help explain the X-ray emissions of distant stars. Understanding flares here informs us about flares on other stars, some of which are far more energetic, the so-called superflares. In short, the sun isn't a done deal in terms of knowledge. We know orders of magnitude more than we did a century ago, but certain puzzles remain, puzzles that keep solar scientists busy and excited. And as we improve our observational tools and our theoretical models, often requiring cutting-edge supercomputers, we edge closer to answering these fundamental questions. It's a journey of discovery, fitting for the star that has always been humanity's primary guide and source. Watching the sun, from ancient eyes to spacecraft journeys. Humans have observed the sun for as long as we've been around, but how we observe it has dramatically changed. What began as naked eye reverence and fear has become a sophisticated, instrument-rich vigil. Let's take a tour of humanity's observation of the sun from the ground to space. In ancient times, people observed the sun's path across the sky and noted patterns, the changing height of the noon sun with seasons, the points on the horizon where it rises and sets shifting over the year, occasional eerie solar eclipses when the sun went dark in daytime, and rare sunrises or sunsets with sunspots visible to the naked eye through dust or haze. They built monuments like Stonehenge or the pyramids at Giza, aligned with solar events, solstices, equinoxes, to mark time. They created solar calendars to guide planting and harvesting, but one did not look directly at the sun, except at sunrise or sunset or through clouds. It was too bright. The invention of the telescope around 1608 changed everything. In 1610, shortly after pointing his telescope to discover moons of Jupiter, Galileo projected the sun's image and saw sunspots. He and others, like Thomas Harriot and David Fabricius, were among the first to record sunspots telescopically. There's also evidence Chinese astronomers had observed large sunspots centuries earlier with naked eye when the sun was dimmed by mist or smoke. Galileo's sunspot observations showed spots come and go and move, indicating the sun's rotation, about one rotation per month. This shattered the old Aristotelian idea of a perfect, unblemished sun and opened the notion that the sun changed over time. For the next few centuries, astronomers tracked sunspots with telescopes. By the 19th century, Rudolf Wolf compiled historical sunspot counts and defined the Wolf sunspot number. In 1843, Samuel Heinrich Schwabe noticed the 11-year cycle in sunspot numbers, the solar cycle we discussed. Solar physics was being born as a field. Spectroscopy came into play in 1814 when Fraunhofer observed dark lines in the sun's spectrum. Later, Kirchhoff and Bunsen realized those lines corresponded to elements, leading to the discovery that the sun and stars are made of chemical elements, and specific ones could be identified, like helium, first discovered in the sun's spectrum in 1868, before found on Earth. Photography, invented in the 19th century, allowed the first photographs of the sun, daguerreotypes in the 1840s, and later, daily photo records of sunspots. Total solar eclipses were also key observational opportunities. In the fleeting minutes of totality, astronomers could see the sun's corona and prominences without the disk's glare. In 1868, spectroscopy of a prominence during an eclipse revealed a new element, helium, named after Helios, the sun god, the first element discovered off Earth. Eclipses also let us study the corona's shape and extent, and they puzzled astronomers. The corona's spectrum had an unidentified line, coronium, which later turned out to be iron at extremely high temperatures, a clue the corona was very hot, though that wasn't understood until much later. Moving into the 20th century, solar observatories like Mount Wilson Observatory in California specialized in daily solar monitoring. George Ellery Hale at Mount Wilson discovered magnetic fields on the sun in 1908 via the Zeeman effect. Sunspots had strong magnetic fields. That firmly established sunspots as magnetic phenomena and opened the era of magnetohydrodynamics in solar physics. By mid-20th century, we started monitoring the sun across more wavelengths using ground-based instruments, e.g., radio telescopes detected solar radio bursts, first noticed in Webby-Wood 2 radar interference, and H-alpha telescopes showed chromospheric flares and filaments. The space age propelled solar observation literally above the atmosphere. Why is that important? Because Earth's atmosphere blocks most UV, X-rays, and gamma rays, and even some infrared. So from the ground, we mainly see visible light, with a bit of near UV and IR. But much of the sun's interesting emissions, like the corona's UV and X-ray radiation, never reach the ground. In the late 1950s and 60s, the first rockets and satellites carrying solar experiments went up. They discovered the solar wind, foreshadowed by comet tail observations, but confirmed by satellites like Luna 1 and instruments by scientists like Gene Parker, who theorized it. NASA's Pioneer and Explorer satellites in the 60s studied solar particles and magnetic fields. The Orbiting Solar Observatory series, 1962 to 1975, carried telescopes, that for the first time continuously observed the sun in UV and X-ray from orbit. They saw the hot corona and its structure outside of eclipse. Humans in space, astronauts on Skylab in 1973-74, had a solar observatory on board. Skylab's Apollo telescope mount captured breathtaking images of the sun in UV and X-rays, revealing arching loops and flares in detail never seen before. We suddenly saw the corona's complexity: loops, holes, coronal holes, regions of open magnetic field associated with fast solar wind, and dynamic events. The 1970s also saw the two Helios probes, a joint US-West German venture, that went closer to the sun, inside Mercury's orbit, and measured particles and fields, precursors to Parker Solar Probe. And Voyager in 1977, though an outer planets mission, eventually crossed the solar wind termination shock decades later, effectively sampling the edge of the sun's influence. In 1980, NASA launched the Solar Maximum mission, focused on studying solar flares. It even had an in-orbit repair by space shuttle astronauts in 1984, an early satellite repair feat. The big leap came in the 1990s and 2000s with SOHO and beyond. SOHO, Solar and Heliospheric Observatory 1995 launch, was a joint ESA-NASA mission parked at the Sun-Earth L1 point, continuously watching the sun. It had instruments for helioseismology to probe the sun's interior by its oscillations, images for the corona in UV, EIT images often seen in green or orange false color, iconic in many articles, a LASCO coronagraph that created an artificial eclipse to observe the corona and CMEs continuously, and which incidentally found over 3,000 comets near the sun. SOHO transformed our monitoring of the sun. We went from sporadic observations to 24/7 coverage. It observed sunspot formation, flow patterns on the surface, and thousands of CMEs, helping tie them to geomagnetic storms. Then came TRACE, 1998, with higher resolution UV imaging, RESI, 2002, observing high-energy X-rays and gamma rays from solar flares, and HINODE, 2006, a Japan, US, UK mission, with high-res optical, UV, and X-ray telescopes to study fine details of magnetic structures. A revolution in seeing the sun's three-dimensional behavior came with STEREO, twin spacecraft launched in 2006. They drifted ahead and behind Earth in orbit, eventually getting views of the far side of the sun and giving us the first simultaneous two-angle look at CMEs, so we could watch these eruptions in 3D. For a while, when stereos were 120 degrees apart, we could see the entire sun's surface at once, no hidden far side. Great for tracking active regions. SDO, Solar Dynamics Observatory, launched in 2010, has arguably the most stunning footage. Ultra-high definition, multi-wavelength movies of the sun updated every few seconds. SDO watches the sun in 10 different wavelengths continuously at high resolution, generating huge amounts of data daily. Its images of solar flares and eruptions in extreme UV are often what you see in science documentaries, glowing loops and waves rippling across the sun. On the ground, new instruments like the Inouye Solar Telescope, opened in 2020 in Hawaii, provide the sharpest pictures of the sun ever in visible light, revealing features as small as 30 kilometers on the sun. We see the solar granulation and fine magnetic elements in exquisite detail. There are also worldwide networks of solar telescopes, like GONG for helioseismology, keeping continuous watch. Recently, we've sent probes quite literally to touch the sun. The Parker Solar Probe, 2018, is diving closer to the sun than any spacecraft in history, using Venus flybys to shrink its orbit. It's already sampled regions where the solar wind is just emerging from the corona. It directly detected the solar wind's magnetic switchbacks and confirmed theories about where the solar wind might get its final push. It will eventually come within about 6 million kilometers of the surface, about 9 solar radii from the sun's center, which is extremely close. At that proximity, Parker deals with sunlight about 500 times more intense than at Earth, hence its revolutionary heat shield. It's giving us in situ measurements of the corona and young solar wind that we've never had. Solar Orbiter 2020 is another major mission, a collaboration between ESA and NASA. It has cameras and instruments to observe the Sun from closer than Earth, about 0.3 AU at closest approach, and at higher latitudes. Over time, it will tilt its orbit up to about 33 degrees, maybe more with future gravity assists, giving a much better look at the Sun's poles, something we've never really seen well. We only saw them indirectly via Ulysses's flyby in the 90s, which had no camera. The poles are important because that's where magnetic fields from old cycles sync and reverse, critical to understanding the solar dynamo. We also maintain a fleet of space weather monitoring satellites. Aside from SOHO and SDO, we have ACE and DSKOVR, monitor solar wind just before it hits Earth, and numerous instruments on other spacecraft that can sense the Sun, e.g., weather satellites often carry particle detectors to measure radiation storms, etc. Even Voyager 1 and 2, at the edge of interstellar space, are measuring the very outer boundary of the Sun's influence, the heliopause. It's worth noting the human element. From 1610 to today, there's been an unbroken chain of people observing sunspots, with only short interruptions. We have over 400 years of sunspot records, one of the longest continuous scientific data sets, thanks to many astronomers over generations. Now, we supplement those with digital data from magnetograms, irradiance measurements. We even measure the Sun's total brightness precisely. It varies about 0.1% over the cycle. Interestingly, the Sun is actually dimmer at solar max in total output, because the many sunspots block light, even though faculae and bright areas compensate somewhat, and other metrics. The result of all this observing power is that we can watch the Sun like a live feed. If a sunspot group emerges, we see it. If a flare erupts, satellites detect the X-rays within minutes, and we get alerts. Coronagraphs watch for a CME cloud. If one is headed our way, we track its speed and predict roughly when it will hit Earth. This has practical benefits, giving warnings to power companies or satellite operators, but also scientific payoff. We catch rare events. For example, SDO might witness a wave called an EIT wave, or solar tsunami, rippling across the Sun after a flare. Or TRACE Hinode might catch the delicate dance of magnetic loops tangling and untangling. We record it all. So, from ancient sun gazers marking shadows to robots literally flying through the Sun's atmosphere, we've radically expanded our solar gaze. It's one of humanity's great achievements that this thing that once was only a source of wonder and fear is now so well monitored that we treat it almost like a familiar, if powerful, neighbor. We routinely incorporate solar data into our daily operations, GPS corrections, satellite drag calculations due to solar activity, heating the atmosphere, etc. And yet, for all this control and knowledge, the Sun still can surprise us. But now, at least when it does, we have front row seats and high-speed cameras rolling. Our journey of watching the Sun is far from over. Future ideas include maybe a solar polar orbiter that goes over the Sun's poles at 90 degrees, or sending specialized satellites to constantly monitor coronal mass ejections from multiple angles to improve space weather forecasts. We might even one day put a telescope on the Moon to monitor the Sun, no atmosphere interference. From fear to understanding, that's been the arc. We no longer think eclipses are dragons eating the Sun. We predict them to the second and chase them to capture images. We don't think sunspots are omens from gods. We measure their magnetic fields and count them to track the Sun's pulse. By observing the Sun, we also sharpened our tools of science historically, developing better telescopes, better detectors, CCDs, etc., better theories. Spectroscopy, quantum mechanics partially came out of explaining spectral lines like those in the solar spectrum. The Sun has been both subject and teacher. And it's profoundly satisfying that the sun, which once inspired myths, now inspires missions. When Parker's solar probe felt the solar corona and sent back data, it was like touching the sun for the first time. Something human imagination has long desired. Legends like Icarus flying too close to the sun come to mind. We found a way to do it and survive, through ingenuity. As our observation continues, we keep weaving a more detailed tapestry of how our star works. Every new wavelength or vantage point adds a piece. And that's not just academic. It feeds back to our understanding of all stars, since the sun is a reference point in stellar astrophysics, and helps secure our societal infrastructure, space weather readiness. Plus, it's just amazing. The images and knowledge remind us the sun is not just a static light, but a dynamic universe unto itself. The future of solar science towards complete understanding. Even with all we've learned, the sun still has lessons for us, and solar science is a vibrant field moving forward. The coming years and decades will likely bring us closer to a complete understanding of how our star works, how it affects the solar system, and by extension, how other stars might affect their planets. What does the future hold? First, we'll be digesting the wealth of data from ongoing missions like Parker Solar Probe and Solar Orbiter. Parker Solar Probe will continue to spiral closer to the sun through 2024-2025, ultimately reaching about 9.86 solar radii, just 4 million miles, from the sun's surface at closest approach. At that distance, Parker will be literally flying through the lower corona, directly sampling the plasma where the solar wind gets accelerated and coronal heating is happening. We expect answers, or at least much better clues, to the coronal heating problem and solar wind acceleration. Already, Parker's data on switchbacks and waves is reshaping models. Solar Orbiter, with its suite of cameras and sensors, will provide context to Parker's measurements, since Parker doesn't carry a conventional camera due to facing the sun. Solar Orbiter will also begin to climb to higher inclinations, up to 33 degrees by around 2027. From that vantage, it will see the sun's polar regions in detail for the first time. The poles are thought to be key to how the sun's global magnetic field reverses every cycle. For example, sunspots usually don't appear near the poles, but magnetic flux migrates there and disappears, sinks inward at cycle ends. We've only inferred what happens via helioseismology. Seeing it directly will be illuminating. On Earth, the Daniel K. Inouye Solar Telescope, DKEST, will be fully operational. Its 4-meter mirror, largest solar telescope, and adaptive optics will allow us to study the sun's surface and lower atmosphere at incredibly fine scales and in various wavelengths, with spectroscopy too. We might resolve the fundamental magnetic building blocks and see how tiny magnetic elements merge to cause flares, or how they shuffle around in granules to generate waves. We'll observe solar features nearly down to the scales where plasma physics microprocesses happen, linking the macro, what we see in large telescopes, to the micro, what Parker might measure in situ. There's also talk of potentially a space-based solar chronograph, like the proposed Solar Probe Plus or Interstellar Mapping and Acceleration Probe has some relevant instruments, to constantly watch the corona without atmospheric interference. Though SOHO's LASCO and the upcoming NOAA SWFO Space Weather Follow-On mission will continue that legacy. In terms of theory, the future is about integration and prediction. We have supercomputers now that can model a star in 3D with some realism. These models are only getting better. Perhaps in the future we'll have a digital twin of the sun. A computer simulation that can, given current data, simulate the sun's behavior and even predict upcoming flares or the next cycle's amplitude. We're far from that now, but progress in computational astrophysics and AI might get us there eventually. Space weather forecasting is definitely a practical goal. In the future, we might have an even more robust network of monitors, Maybe a dedicated far-side monitor at the Lagrange point behind the Sun, so we're never blind to sunspots emerging on the far side. Or monitors at midpoints between the Sun and other planets to see CMEs from different angles. NASA and other agencies are actively planning improved space weather infrastructure because our reliance on technology keeps growing. On the science front, unanswered questions like the solar cycle irregularity might benefit from studying sun-like stars. There's a field called solar-stellar connection, observing sun-like stars at different ages to see how their activity levels and cycles differ. This gives insight into our sun's past and future. For example, older stars might show longer cycles or weaker activity, informing how the sun might behave as it ages, though it will be stable for a long time. Younger sun-like stars show wild activity, superflares 1000x bigger than the biggest solar flares. Our sun likely did that in its youth. Understanding that helps understand early Earth conditions. We've solved the solar neutrino problem in terms of physics, but neutrino detectors are still improving. Future neutrino observatories might even be able to monitor the sun's core in real time, like detecting changes in fusion rate if they happened, though we don't expect quick changes, but it's a tool to see the deep core indirectly. Another frontier, in situ measurements closer to or even inside the sun. Parker is already doing daring work. One could imagine future probes even more advanced, maybe something that could take high-res images from closer in, though heat protection and data transmission are challenges. Or even dropping probes into the sun, like how we drop probes into Jupiter's atmosphere. Though surviving much beyond the very outer layers is likely impossible with foreseeable tech. When the sun is more active, like the upcoming solar cycle 25 peak around 2025-2026, all these observatories will have a chance to capture major events with unprecedented clarity. It's like having an array of high-speed cameras for the Olympics of solar activity. We might catch a once-in-decade scale event, not that we wish for a super flare, but if it happens, we're far better equipped now to study it than ever. Looking further, human exploration might also bring new solar observations. For instance, astronauts on the Moon could set up advanced solar telescopes on the lunar far side, no Earth radio interference and a stable platform, or near side with quick communication to Earth. The Moon could host a coronagraph or radio array for solar monitoring. Also, as we plan crewed missions to Mars, monitoring solar radiation events becomes directly life-critical, so there'll be investment in that predictive capability. Then there's the synergy with heliophysics in general. The Sun-Earth system is one piece, but the Sun's influence extends to the heliosphere boundary, as Voyagers showed. As the Voyagers and New Horizons measure the outer heliosphere, and IBEX and IMAP, Interstellar Mapping and Acceleration Probe, image the heliosphere's interaction with the interstellar medium, we're completing the picture of the Sun's domain. In the future, perhaps a dedicated interstellar probe might measure the heliosphere from outside in detail. So, future solar science isn't just about the Sun in isolation, but the Sun as the central engine of a connected system, from its core to the cosmic ray boundary. It's truly holistic now. Philosophically, one might ask, can we control or mitigate the Sun's effects if needed? We can't change the Sun's output. It's far beyond our technology, or should we ever attempt such a thing. But if, say, in the far future, greenhouse warming from the Sun becomes an issue, maybe distant descendants could do geoengineering to counter it. Conversely, if a future grand minimum caused slight cooling, we could adapt. Those are speculative and minor compared to anthropogenic effects now, but interesting in the very long term. The ultimate far future, billions of years. Perhaps humanity, or our successor species, might consider moving the Earth or migrating elsewhere when the Sun really starts to go bad. It's been suggested that a civilization could use gravity assists with asteroids to gradually expand Earth's orbit to keep it in the habitable zone longer, or build habitats around outer planets. These are ultra-long-term musings, but it shows how knowledge of solar evolution might be actionable in the far, far future if intelligence endures. On a nearer horizon, the knowledge we gain about the Sun also feeds into understanding exoplanets. When we find an exoplanet in the habitable zone of a star, we have to consider that star's behavior. Is it a quiet star like the Sun or a flare star? Knowing how different stars behave, based on analogies to solar behavior under different conditions, helps us assess which exoplanets might have stable climates or retained atmospheres. The Sun is our only star we can study in such detail to inform these models. So, the future of solar science is both about solving the physics puzzles of our Sun and applying that understanding broadly. We'll likely see a refinement of our models to the point where we can say, for instance, exactly how the Sun will behave next year or next cycle with some statistical confidence, and where we can accurately simulate the emergence of a sunspot from deep within the Sun to its flare and CME production, essentially mastering the understanding of stellar magnetic activity, a tremendous physics triumph when it happens. And of course, every time we think we've got it all, nature can surprise us. The Sun has certainly humbled scientists before, e.g., the unexpected existence of the solar wind came as a surprise to many mid-century scientists, or the neutrino problem earlier. But we have more tools than ever to address surprises. We're also training new generations of solar scientists, and the field is growing more interdisciplinary. Blending plasma physics, data science, machine learning is being applied to solar flare prediction, for example, astrophysics, and even planetary science for sun-planet interactions. In essence, while the Sun's been observed by humans for millennia, one could argue we are entering a golden age of solar astronomy. Never before have we had such a comprehensive set of instruments in space and on the ground, and powerful computational tools, all focused on unraveling our star. The resulting knowledge will not only satisfy human curiosity, a worthy goal in itself, but also help protect our technological society and inform us about our place in the universe. The Sun and Earth's history, climate and human tales, written in sunlight. Our Sun has been a steady companion to Earth, but it is not absolutely constant. Changes in the Sun's output over time have left subtle fingerprints on Earth's climate and possibly on human history. Figuring out the Sun's role in past climate changes is like detective work. The Sun is one factor among many: volcanoes, atmospheric composition changes, orbital cycles, etc. And its influence is usually not the dominant one in recent times. But if we look at history and prehistory, patterns emerge where the Sun's variability may have nudged the climate. On very long timescales, millions to billions of years, the Sun's brightness has increased significantly since Earth's formation. We mentioned the faint young sun paradox earlier, the fact that the Sun was 30% dimmer 4 billion years ago, yet Earth wasn't a permanent ice ball. The resolution is largely that Earth's atmosphere must have had a lot more greenhouse gases, like CO2 and methane, early on to trap heat, compensating for the dimmer Sun. Over time, as the Sun brightened, CO2 levels decreased through processes like rock weathering and carbon burial, aided by life, and natural negative feedback maintaining Earth's habitability. So in that sense, life and geology co-evolved with the Sun's slowly changing luminosity, keeping Earth in the Goldilocks zone. If Earth had not adjusted its atmosphere, it could have frozen solid initially or overheated later. This interplay is crucial in understanding long-term climate stability. On shorter timescales, centuries to millennia, the Sun's impact is more subtle, but scientists have identified a few noteworthy periods. The most famous is the Little Ice Age, roughly 1300 to 1850 AD, though definitions vary. It was a time of generally cooler temperatures, especially in the northern hemisphere, with advances of mountain glaciers, colder winters, etc. Within that period, the Maunder minimum, 1645 to 1715, stands out, a time with very few sunspots observed. It coincided with some of the coldest decades of the Little Ice Age. While the exact temperature drop attributable to the Maunder minimum is debated, volcanic activity and natural climate variability also contributed to the Little Ice Age. Climate models that include a slightly dimmer sun during that time do produce some cooling. Sunspot observations, later backed by carbon-14 isotope data, which is inversely correlated with solar activity, suggest the sun's output was a tad lower, not drastically, maybe 0.2–0.3% less bright. This likely cooled the Earth a bit, especially regionally. Europe and North America saw hard winters, etc. Some historians link these harsher conditions to things like crop failures, which can fuel social unrest, e.g., some speculate that the cold period in the early 1600s contributed to famines and perhaps the uprisings in Europe, or that a later cold wave in the 1780s, mid-Little Ice Age, contributed to pre-revolution hardship in France. However, one must be cautious. Societal events have many causes, but climate can be a stressor. Another period, the medieval climate anomaly, or medieval warm period, roughly 950 to 1250 AD, saw slightly warmer conditions in parts of the world, not globally uniform. This has been loosely associated with a time of relatively high solar activity, medieval maximum. Sunspot estimates suggest the sun was active then. That, plus low volcanic activity, might have given a small warming bump. It's debated how pronounced it was globally. Certainly not as warm as today's anthropogenic warming, but it may have helped Norse Vikings farm in Greenland, and wine grapes grow in England a bit more easily, for instance. These links between solar activity and climate are subtle because the sun's variations are small compared to the effect of greenhouse gases. But we do see some correlation over the last millennium. For example, higher carbon-14, which means lower solar activity, since high solar activity deflects cosmic rays that produce carbon-14, aligns with cooler periods in some data. In more recent times, last 150 years, we have direct measurements of the sun's irradiance only since 1978 via satellites. They show the hecti.1% solar cycle variation and possibly a slight declining trend from cycles 21 to 23, then a small rebound in cycle 24. Meanwhile, global temperatures have risen strongly. Studies show the warming since 1900 is overwhelmingly due to greenhouse gas emissions, with solar changes contributing at most a minor fraction. Some estimates say solar contributed maybe 5 to 10% of early 20th century warming, and near zero of late 20th century warming. In fact, since about 1950, solar activity hasn't trended upward. If anything, it plateaued and even declined slightly after 1990. So the sun cannot explain recent global warming. This is a critical point. While the sun influences climate, it has not been the cause of the recent warming. We know that because we can measure what the sun's doing, and it hasn't increased net output in the past 50+ years. However, understanding solar influence is still important for climate science, to properly attribute past changes and refine climate models. For instance, an upcoming low solar activity period. Some speculated we might go into a grand minimum, though that hasn't happened so far. Cycle 25 is looking fairly normal, might cool the Earth by 1/10 of a degree or 2/10 at most, which would only slightly offset anthropogenic warming, which is much larger. It's good to gauge that precisely. Another interesting connection: cosmic rays and clouds. Some researchers hypothesize that during low solar activity, when more cosmic rays reach Earth's atmosphere, since the sun's magnetic field is weaker, increased cosmic rays might seed more clouds through ionization, which could cool climate. Clouds can reflect sunlight. This idea, championed by Svensmark and others, is intriguing, but remains unproven in a significant way. Empirical evidence for strong cosmic ray cloud links is mixed. If it exists, it's likely small. The CERN cloud experiment is investigating this in a controlled way. So far, It looks like cosmic ray changes from solar cycles likely don't dominate cloud formation compared to other factors, like aerosols from volcanoes or pollution. It's an area of ongoing research, though. Switching from climate to more direct human impacts, the sun's variability has made it into historical records in other ways. People noted red skies, likely auroras, in chronicles, like the Carrington event, auroras, in 1859, being seen in Cuba, Rome, etc. They noticed when the sun had spots. There are ancient mentions of visible sunspots, e.g., during the Carolingian period around 807 AD, records of a black spot on the sun visible at sunrise, likely a large sunspot group. But they couldn't interpret them scientifically. One could ask, did the 11-year solar cycle ever affect things like agriculture? There's tentative evidence that in some regions, solar cycle variation might influence rainfall patterns slightly, through complex atmospheric responses to UV changes perhaps. For example, some studies suggest a weak tendency for more rain in certain tropical areas at one phase of the solar cycle. Nothing one could plan farming around reliably, though. On really long scales, as the sun brightens further, hundreds of millions of years future, Earth will enter a moist greenhouse state, as we discussed, and then a runaway greenhouse, water-lost, Earth-like Venus, maybe around 1 to 2 billion years from now. That's more about the eventual fate of the biosphere under a warming sun. But interestingly, some think the sun's gradual brightening helped end past snowball Earth episodes, periods in Earth's deep past when most of the planet was glaciated. Earth may have frozen over a couple of times 700 million years ago, and getting out of that snowball could have been nudged by volcanic CO2 buildup, but also the sun's slight increase in luminosity by then compared to earlier epochs. In human terms, the sun's constancy has been a blessing. Civilization arose during a time of fairly stable solar output, Holocene epoch. That said, some link the Roman warm period, 1 AD, or the Dark Ages cold period, 600 AD, partly to solar changes, but those links are not as clear as the medieval LIA ones. It shows how other factors, like big volcanic eruptions or ocean cycles, can overshadow solar influence at times. What about the future? We are studying whether the sun might enter another grand solar minimum this century. Some solar physicists had speculated reduced cycle amplitude could happen. There was a relatively weak cycle 24, leading to talk of a Maunder minimum repeat. Cycle 25 so far is stronger than 24, so it doesn't look like we're plunging into a Maunder-like minimum immediately. But if we did, climate models indicate it would offset maybe 0.1, 0.2 degrees C of warming, a tiny blip against ongoing anthropogenic warming, delaying it by a few years at most. So, no mini ice age is expected from a solar lull alone. It's interesting to note that even though solar variations aren't causing current climate change, understanding them is still important to refine climate models. These models include solar forcing as one component. If we ever see unusual solar behavior, like an extended period of no sunspots, we'd want to factor that in to near-term climate projections. On societal timescales, the direct impact of solar variability nowadays is mostly through space weather, as discussed, rather than climate. But historically, one could argue that poor harvests in the late 17th century Maunder minimum contributed to, e.g., the collapse of certain settlements. Greenland's Viking colony died out by early 1400s, partly due to cooling climate. The year without a summer in 1816, which caused famines in Europe, was actually due to a volcano, Tambora, though it happened during the Dalton minimum, a moderate solar minimum, which perhaps made it slightly worse. We've also tried to tie solar cycles to things like animal behavior, or even economics. There have been fringe claims that sunspots affect human psychology or markets. Most of those are not scientifically supported. There was a 19th century belief, for instance, that sunspot cycles influence commodity prices, largely coincidental patterns. We're more cautious now with correlations. One tangential but interesting historical note. In the late 1800s, some speculated that the sun might be variable enough to cause another ice age soon, which worried people. That was an overestimation of solar variability. They didn't know about CO2 warming offsetting things either. Ironically, now our worry is the opposite, warming, and we know the sun isn't the culprit for the current trend. In summary, the Sun-Earth history is a tale of a star that has thankfully been stable enough for life to flourish, with small wobbles that have occasionally tweaked the environment. By studying tree rings, ice cores, and other proxies, scientists piece together past solar activity and climate responses. It's like reading the sun's diary and Earth's diary side by side to see where they align. Finally, thinking on very long perspectives. As the sun ages and Earth becomes less hospitable, if intelligent life is still around, the slowly brightening sun will be an impetus to find solutions, whether moving further out or technological fixes. It's poetic that while we worry about immediate issues like the next decade or century, our planet's life zone is ultimately transient on geologic timescales. The sun giveth, and the sun will eventually taketh away. But that's a few billion years ahead, a reminder that nothing in the cosmos is truly permanent. For now and the foreseeable future, the sun is our reliable, life-nurturing star. Its variations, though minor compared to human influences now, have played a part in the background of Earth's story. Understanding those helps complete our picture of Earth's climate puzzle and also satisfies our curiosity of how our star has influenced the fate of civilizations in subtle ways. The lifespan of a sun, from stellar cradle to grave. Stars like our sun have life stories. They are born, they live long, steady lives, and continued. They die. While the timescales and details differ from living creatures, the analogy is fitting. Let's journey through the typical life cycle of a star like our sun, from birth to demise, to see how it transforms over billions of years. Birth, from cloud to protostar. Every star begins in a stellar nursery, a giant molecular cloud of gas and dust in space. These clouds are cold and dark. Over time, a disturbance, perhaps a shockwave from a nearby supernova or a collision with another cloud, causes a region of the cloud to start collapsing under its own gravity. As this region contracts, it breaks into smaller clumps, each destined to become a star. In each clump, material falls toward the center, which grows denser and hotter. This forming object is the protostar. It's not a true star yet. It's more like a hot, dense core at the center of a collapsing cloud, still gathering mass. It may be surrounded by a disk of gas and dust, the raw material for future planets. The protostar stage lasts tens of thousands to a few million years. Eventually, the core of the protostar becomes hot and pressurized enough for the next leap. Ignition. A star is born. When the core temperature of a protostar reaches about 10 million degrees C, hydrogen nuclei begin to fuse into helium. This marks the onset of nuclear fusion and the birth of a star. For our sun, this probably happened within 50 million years of the collapse starting. Fusion releases a torrent of energy outwards. This energy creates an outward pressure that counters gravity. The young star settles into a balance, hydrostatic equilibrium. It also blows away remaining excess gas and dust around it, with intense stellar winds and radiation. What's left is a newborn star with perhaps a protoplanetary disk around it. At this point, the star joins the main sequence, the long, stable phase of stellar life. Main sequence. The long, steady adulthood. A star like the Sun spends roughly 90% of its life as a main sequence star, quietly fusing hydrogen into helium in its core. Our Sun has been in this phase for 4.6 billion years and will remain for about another 5 billion. On the main sequence, a star's properties stay fairly constant. The sun slowly gets brighter over time as its core changes. As noted, it's about 30% brighter now than when it formed. But from our perspective, over millennia, it doesn't change dramatically. It shines steadily, providing consistent warmth. For a star, this is its adult life. Robust, stable, long-lasting. Stars much more massive than the sun live fast and die young. They burn hot and exhaust their fuel in only millions of years. Stars, less massive, like red dwarfs, sip fuel so slowly they can live for hundreds of billions or even trillions of years, far longer than the current age of the universe. Our sun's pace is moderate. Over the main sequence, the core gradually accumulates helium ash, and the fusion region slowly moves outward. The core's composition and conditions evolve, causing that slow increase in luminosity we discussed. Eventually, however, the hydrogen in the core will run low. For the sun, after about 10 billion total years of main sequence life, the core can't sustain hydrogen fusion. This is the beginning of the end for the sun's steady phase. Leaving the main sequence, subgiant to red giant. When core hydrogen is exhausted, fusion there ceases. Without outward pressure from core fusion, gravity begins to collapse the core. As the core contracts, it heats up. Gravitational energy converts to heat. This ignites hydrogen in a shell around the core. Hydrogen that's in a layer just outside the now helium core starts fusing. That shell fusion actually releases more energy than the core fusion did. This extra energy pushes the sun's outer layers outward tremendously. The sun begins to expand and cool at the surface, turning into a subgiant and then a red giant. In this red giant phase, which for the sun will occur about 5 billion years from now, the sun will become enormous, perhaps on the order of 100 times its current diameter or more. It will swallow the inner planets Mercury and Venus. Earth's fate is uncertain. It may survive just outside the swollen sun, or it may be grazed or engulfed. In any case, Earth will be roasted, oceans long boiled away by that point. As the sun's radius grows, its surface temperature drops to maybe 3,000 degrees, hence the redder color. But its total luminosity skyrockets due to the huge surface area. It will shine several thousand times brighter than now. Imagine the sun taking up half the sky, glowing dull red. That will be the view from what's left of the solar system. Perhaps the icy moons of the outer planets will briefly enjoy a warm glow. Some speculate that in the distant future, humans might colonize places like Titan or Pluto during the sun's red giant phase as those places warm up. Purely speculative fiction at this point. Inside the red giant sun, the core continues to contract and heat up because it's now mostly helium and not yet hot enough to fuse helium. Eventually, the core reaches about 100 million degrees C. Suddenly, helium fusion ignites in the core. For sun-like stars, this happens in a flash, the helium flash, a runaway brief event that then settles. Now the sun has found a new fuel. It fuses helium into carbon and some oxygen in the core. The energy output actually drops compared to the shell-burning phase, so the sun's giant outer layers shrink a bit from their maximum red giant size. The sun moves to the horizontal branch of the Hertzsprung-Russell diagram. It's now a more stable helium-burning star, perhaps a few tens of times larger than today and much brighter than today, but smaller and slightly hotter than it was at peak red giant. This helium-burning phase lasts a much shorter time, maybe on the order of 100 million years. The sun will fuse helium into carbon and oxygen in its core until helium runs low. Meanwhile, it likely still fuses hydrogen in a shell around the core as well. Once helium in the core is exhausted, the core is now carbon and oxygen. The sun, being not massive enough, you need 8 solar masses or so initially to do more, cannot ignite carbon fusion. So what happens? The core contracts again. The outer layers respond by expanding again. The sun swells into a second giant phase. Specifically, an asymptotic giant branch star. It becomes extremely large and luminous again, perhaps even more so than the first red giant phase. However, it's highly unstable now. The Sun will begin to pulsate and shed its outer layers. Each pulsation or thermal pulse can blow off huge amounts of mass. Over several tens of millions of years, the Sun will lose a substantial fraction of its mass. The solar wind at this stage becomes a gale that carries away the Sun's envelope. What's happening is the Sun is in its death throes, casting off the outer layers that can no longer be held by its weakening gravity. Since the core is contracting and the overall binding is weaker for the puffed up outer parts. Eventually, the Sun's outer layers are largely expelled into space, revealing the hot core within. This exposed core is small, roughly Earth-sized, and extremely hot, 100,000 degrees Celsius or more at the surface initially. It pours out ultraviolet radiation. The expanding outer layers, now removed, form a glowing shell of gas around the Sun's core. This is the formation of a planetary nebula, one of those gorgeous cosmic structures we observe around other dying stars, like the Ring Nebula or Helix Nebula. The name planetary nebula came from early astronomers who thought these round gas clouds looked a bit like planetary disks in their telescopes. Our Sun will create such a nebula, a final cosmic artwork, with rings or shells of multicolored gas, depending on how the mass loss occurs and the elements present. This nebula will last only perhaps 10,000 to 20,000 years before dispersing into the interstellar medium, mixing its substance with the galaxy. What remains at the center is the Sun's former core, now a white dwarf. This white dwarf will contain roughly 0.5–0.6 of the Sun's original mass. The rest was lost in the nebula, packed into a sphere about the size of Earth. It is made primarily of carbon and oxygen nuclei immersed in a sea of degenerate electrons. It's basically an extremely dense crystal-like state of matter. There is no fusion going on. The white dwarf shines from residual heat. It's incredibly hot when formed, so it glows white-blue initially. Over billions of years, it will cool down, turning yellow, then red, then infrared, and eventually becoming a cold, dark, black dwarf. Though again, the universe isn't old enough for any to have cooled that much. This white dwarf Sun will be the corpse of our star. It will sit in the middle of a faint expanding halo of gas, the remnants of the planetary nebula, which eventually becomes just part of the general interstellar gas. Any remaining planets, likely the outer ones like Jupiter, Saturn, etc., which might drift farther out due to the Sun's mass loss, will now orbit this small, dim cinder. The solar system as we know it will be gone. Only perhaps some icy bodies and gas giant cores remain, orbiting far from a white dwarf that once was the brilliant Sun. While this sounds melancholy, it's the natural life cycle of stars like the Sun. And importantly, the Sun's death will return material to space. The carbon and oxygen made in the Sun's core, plus any unprocessed heavier elements the Sun had, will be blown into space to become part of future stars and planets. The Sun is a second-generation star. It contains heavier elements from prior stars' supernovae. Likewise, it will contribute to a third generation. The carbon in your body might one day be part of the soil of a new world around a new star, thanks to the Sun's final act of dispersal. For an even broader perspective, lower mass red dwarf stars won't go through such a dramatic phase. They'll last trillions of years and end quietly as dim, white dwarfs, never swelling into giants. Higher mass stars, above 8 solar masses, will die far more violently in supernova explosions, leaving neutron stars or black holes. The Sun is in the intermediate category of stars that die gently, relatively speaking. No supernova awaits the Sun. It's not massive enough. Instead, it's a beautiful planetary nebula and a white dwarf destiny. When we look at nebulae through telescopes, we are effectively seeing the future fate of our Sun. It gives a sense of continuity in the universe. Stars are mortal, but their matter gets recycled. Now, in practical terms, all this is far in the future, but it has implications for life. As discussed, Earth will face uninhabitability way before the grand finale, due to the sun's brightening. So the timeline might be, in 1 billion years, Earth becomes a hothouse, and life as we know it likely perishes or has to escape. In 5 billion years, the sun goes red giant and possibly engulfs Earth entirely. In 5.1 billion, the sun ignites helium. By 5.5 billion, it sheds into a planetary nebula. By 5.5+ billion, the sun is a new white dwarf, slowly cooling for eternity. The solar system's architecture will change. The habitable zone will move outward during the giant phases. Perhaps for a time, moons of Jupiter or Saturn could experience Earth-like temperatures, though the intense luminosity might strip atmospheres. It's a dramatic, albeit short, opportunity. Tens of millions of years, which is short for evolution of complex life. But who knows, maybe extant life on outer moons could take advantage. After the nebula fades, the sun's remnant will cool and the solar system will be dark, lit only by the feeble glow of the white dwarf, which would be as luminous as, say, a bright planet is to us now. Eventually, the white dwarf may cool to the point of not emitting visible light, just a cold sphere with maybe some exotic crystals in its core. White dwarfs might eventually crystallize like a gigantic diamond of sorts. All of this reminds us that stars like the sun are cosmic forges and also temporary havens. For now, the sun is kindly. It provides steady energy. In the far future, it becomes a destroyer, from our perspective, and then a remnant. But that far future is beyond human scales. In the meantime, humanity's challenge, assuming we're still around, is to figure out space travel long before our sun becomes a threat. Perhaps any spacefaring civilization in the solar system 1 billion or more years hence would move to the outer solar system or to another star system entirely. It's poetic. We come from stardust, elements from previous stars. We're sustained by our star, and ultimately, we, or our atoms, will return to interstellar stardust when the sun dies. Life, at the most fundamental level, is the universe's way of making temporary use of the energy of a star, before returning that energy and matter back to the cosmos. Beyond our sun, a menagerie of stars. While we've focused on our sun, it's just one of countless stars. To truly appreciate the sun, it helps to see it in context among the diverse menagerie of stars in our galaxy. Stars come in an incredible range of sizes, masses, colors, and lifetimes. The sun happens to be a fairly average star. Let's briefly tour the stellar zoo. Red dwarfs, small and cool. These are the most common stars in the Milky Way. They are smaller than the sun, from about 0.1 to 0.5 times the sun's mass. They shine much dimmer and cooler, often with a reddish hue because their surface temperatures are only 2,500 to 3,500 degrees compared to the sun's 5,500 degrees. A red dwarf might emit just 1% or less of the sun's light. Because they burn their hydrogen so slowly, red dwarfs live extraordinarily long, tens to hundreds of billions of years, far longer than the current age of the universe, 13.8 billion years. In fact, none have died yet. Even the oldest red dwarfs are still on the main sequence. If Earth orbited a red dwarf at the right distance, much closer in, since they're faint, the sun in its sky would be a dim red glow, and likely tidally locked, one side always facing the star. Red dwarfs can be very flare-active. Some emit powerful flares that could strip atmospheres of close-in planets, which is a concern for the habitability of red dwarf systems. Still, many exoplanets have been found around red dwarfs, including some near the habitable zone, like the famous TRAPPIST-1 system. Red dwarfs show that not all stars are as stable and gentle as our sun. Some have very rambunctious space weather. Blue giants and supergiants, massive and hot. On the other extreme, we have stars much more massive than the Sun. O-type stars, for example, might be 20, 30, 50 times the Sun's mass, even up to 100 plus in rare cases. They burn incredibly brightly with a blue-white color, surface temperatures 20,000 to 40,000 degrees or more. A single O-type star can outshine millions of suns and can be seen across great distances. However, they burn out quickly, maybe in a few million years. They typically end their lives in violent supernovae, exploding and leaving neutron stars or black holes. Because they emit so much high-energy radiation, any planets around them, if any could even form and survive the harsh environment, would be blasted by UV and X-rays. The Sun is modest in comparison, but interestingly, the Sun is brighter than about 90% of stars, because the majority are those faint red dwarfs. It's like a mid-sized car in a world where most vehicles are mopeds and a few are monster trucks. Binary stars and others. Many, if not most, stars come in binary or multiple systems. Two or more stars gravitationally bound, orbiting each other. Our Sun is solitary, which is a bit fortunate for us. Multiple stars can make planetary orbits complicated or unstable. In binaries, sometimes you get exotic interactions. One star can steal mass from another if they're close, leading to novae, surface explosions on white dwarfs, or X-ray binaries, neutron star or black hole pulling material from a companion. There are also variable stars. Some pulsate regularly, like Cepheid variables, brightening and dimming with a rhythm. The Sun is relatively steady. It doesn't have large intrinsic brightness swings. Giants and dwarfs. After the main sequence, as we saw with our Sun's future, stars become giants or supergiants. There are red giants, like Betelgeuse, and even larger blue supergiants, like Rigel in Orion. And at the small end, there are the stellar remnants, white dwarfs, neutron stars, black holes. White dwarfs, as discussed, are the end state of Sun-like stars, hot, Earth-sized embers. Neutron stars, city-sized, incredibly dense, and black holes are born from supernovae of massive stars. Comparing to the Sun is a G-type main sequence star, spectral type G2V. In the classification OBAFGKM, from hottest to coolest main sequence stars, the Sun is roughly in the middle, G. Stars like Sirius, A-type, are hotter and bigger. Stars like Proxima Centauri, M-type red dwarf, are much cooler and smaller. Why does this matter? Understanding other stars highlights how special our Sun is to us, and also how it is one example of a continuum. For instance, the Sun has a relatively low magnetic activity compared to many similar stars. Some Sun-like stars have bigger cycles or more frequent flares, yet it's active enough to have sunspots and auroras, perhaps a Goldilocks level of activity that allowed life to develop without too much disruption. The Sun is single, no companion star to complicate our orbit or perturb comets to send too many our way, though our Sun's galactic environment still does that occasionally. In terms of age, the Sun is middle-aged. Stars much older than the Sun, often orange-ish K-type stars, might be stable, long-lived lights around which ancient life could exist, if conditions are right. Younger stars often have more eruptions and variability. By studying other stars, we also gain insight into the past and future of the Sun. Young suns, Sun-like stars a few million years old, are often surrounded by disks and are far more active, with frequent big flares. Our Sun likely was like that, which might have impacted early Earth, or at least the chemistry of the early solar system. Old suns, subgiants or giants that used to be Sun-like, show us what's to come in terms of size and brightness and composition changes. Numbers. About 75% of stars in our galaxy are M-dwarfs, red dwarfs. About 5% are Sun-like, F and G-type. The rest are either slightly smaller K-types or bigger, A, B, O types. The O and B are extremely rare. So the Sun is in a minority in terms of brightness, but not extremely rare either. It's often called a yellow dwarf, though the Sun's color is white. It appears yellowish from Earth due to scattering. We've even found exoplanets around various types of stars, and this is where comparisons become practical. A planet around a red dwarf, for instance, will experience a very different stellar environment, likely tidally locked, possibly receiving flares. A planet around an F-type star gets more UV radiation, could affect life's DNA. Our sun's characteristics have influenced everything from the colors of plants, optimized for the sun's spectrum, to the rhythms of life, 24-hour rotation lit by the sun. In the end, studying the stellar zoo underscores that our sun, while average, gave us very fortunate conditions. If the sun were a bit more massive, type F, it would burn out sooner and perhaps be too bright initially. If less massive, type K or M, Earth would have to be closer. Tides could lock Earth's rotation, or the star's flares could be harsher. The sun seems nicely suited to long-lived, stable habitability. It's like we hit the jackpot. Not too hot, not too cool. A main sequence star that stays calm for billions of years. This awareness also fuels the search for life elsewhere. We often target sun-like stars in SETI and exoplanet searches, thinking they might offer similar stability. For instance, the Kepler mission found some Earth-sized candidates in sun-like star habitable zones like Kepler 452b, dubbed an older cousin of Earth. But we also expand to other types, because perhaps life could adapt to a dim red sun or a bright white sun differently. In summary, beyond our sun lies a cosmos full of other suns, each with its own story. By comparing them, we learn that our sun is moderately sized, middle-aged, single, and reasonably well-behaved, which is a lucky combination for us. It's one star among billions, yet for us, it's unique. The diversity of stars also shows what might have been. Had our sun been different, our fate would be different. It also hints at what's possible elsewhere. Countless stars means countless opportunities for planets, and maybe life under very different stellar lights. Alien suns and the possibilities for life. When we gaze at the night sky's stars, we are effectively looking at other suns, each potentially with its own retinue of planets. In recent decades, we have confirmed that planets abound around other stars, exoplanets. This raises the tantalizing question: could there be other worlds warmed by their suns where life thrives? To ponder this, we must consider how different alien suns, stars, might affect the habitability of their planets. The habitable zone of a star, the range of distances where a planet might have liquid water on its surface, depends on the star's luminosity. Our sun's habitable zone currently spans roughly from about 0.95 to 1.4 AU, astronomical units, where 1 AU is Earth's distance. But for a dimmer star, the zone is much closer in. For a brighter star, it's farther out. One interesting consequence: planets in the habitable zone of red dwarfs, M stars, have to orbit very close to the star, often at distances of 5 to 20% of an AU or even less. At those distances, tidal forces from the star would likely lock the planet's rotation, meaning the planet keeps one face always toward the star, similar to how the moon is tidally locked to Earth. This could cause one extremely hot side and one cold, dark side. However, if the atmosphere or oceans can redistribute heat, a habitable twilight band or global habitability is possible in theory. Red dwarf planets would experience a very different sky. The star looms large and red, and days might be perpetual if locked, with a stationary sun in the sky on the day side. Also, red dwarfs often flare. A habitable planet would need to endure those flares. It might need a strong magnetic field or thick atmosphere or ocean to protect life from radiation. Despite challenges, red dwarfs have become a focus in the search for life because they are so numerous, and their small size makes detecting Earth-sized planets easier. Transits and radial velocity signals are more pronounced. The TRAPPIST-1 system, for example, has 7 Earth-sized planets, several in or near the habitable zone. If life can adapt to a dim red sun that occasionally flares, maybe one of those could host life.
life might look different, perhaps using infrared light for photosynthesis, if at all, maybe huddled underwater during flares.
Around stars a bit smaller than the Sun, say K-type stars, orange dwarfs, the habitable zone is a bit closer than Earth's distance, and these stars are often very stable for very long times, even longer main sequence lifespans than the Sun's high 10 billion years, maybe 20-30 billion. That could be excellent for giving life plenty of time to develop and evolve. Some astrobiologists think K-dwarfs might be prime targets for finding life, as they offer a balance of stability and longevity. Around stars more massive than the Sun, like F-type stars, the habitable zone is farther out, and these stars emit more UV. Life on a planet around an F-star might have to contend with stronger UV radiation. Maybe thicker ozone layers would develop. But the window for life is somewhat shorter because F-stars burn out in a few billion years. It's possible intelligent life could evolve faster, but it's a tighter schedule. Still, it's not impossible. Then there are exotic possibilities. Binary star systems where a planet might orbit around two stars, circumbinary planets. We know they exist. Kepler 16b was the first discovered, nicknamed Tatooine planet. If both stars are relatively small, a stable habitable zone orbit can exist. The sky on such a planet could have double sunsets. Spectacular. But the climate might be a bit more complicated with two sources of light and gravity. Yet, nature manages as long as the orbit is not too erratic. Giant stars, like a planet around a red giant, would have a habitable zone that moves outward as the star evolves, not a stable situation long-term, though maybe temporarily an icy moon could thaw. Some have suggested that when the Sun becomes a red giant, outer solar system moons might warm enough to be habitable for a short time. Neutron stars, or white dwarfs with planets. These are extreme, but there's speculation about life around white dwarfs. Right after a white dwarf forms, it's very hot and luminous. A habitable zone could exist for a few million years while it cools through the right range. But that's short. Still, interesting to consider if life could briefly flourish on a world warmed by a fading ember of a star. From a philosophical perspective, when we think alien suns, we imagine perhaps living beings under a different colored sky. If a creature evolved under a red dwarf's perpetual twilight, how might it perceive the universe? Or under a very blue star, would their vision adapt to UV, or would they shelter in water from the harsh rays? Even things like plant pigmentation could differ. On an Earth-like planet around an F-star, plants might reflect more UV and appear very yellow or orange to cope with the star's spectrum. Around an M-star, plants might be nearly black to soak up all available light, since red dwarfs put out mostly infrared and red light. The sun and its light have shaped our biology. Our eyes are most sensitive to yellow-green, where the sun's output peaks. Plants use red and blue light heavily because the sun provides a lot of it, etc. On other worlds, senses and ecosystems would tune to their star. We often call these stars suns from the perspective of any potential inhabitants. To them, our sun is just another star in their sky. It's an intriguing symmetry. We revolve around our sun and wonder if someone around another star looks at our sun and wonders if anyone is here. In our search for extraterrestrial life, we initially focused on stars like the sun, reasoning that's what we know. But we've expanded to the whole spectrum of possibilities. NASA's Kepler and TESS missions have found thousands of exoplanets at all sorts of stars. So far, we haven't confirmed an Earth twin, an Earth-sized planet in the habitable zone of a sun-like star with a roughly 1-year orbit, though there are candidates. We have found Earth-sized planets in the habitable zones of dimmer stars. Could life exist in forms very different from ours, around suns very different from ours? Possibly. Astrobiologists consider, for example, that if a star emits a lot of UV, life might evolve protective mechanisms like biofluorescence, using harmful UV and re-emitting it as visible light. Or life might thrive underground or underwater to avoid surface radiation, coming out during quieter periods of the star. Or on a tidally locked world, life might exist mainly in the twilight band between day and night sides. The Drake equation for estimating intelligent civilizations includes a term for the fraction of stars with habitable planets. Given what we know now, planets are very common, and many stars, especially long-lived ones like K, G, maybe M types if flaring isn't prohibitive, could have habitable worlds. It suggests there could be numerous alien Earths with their own suns. Whether life arises often is still unknown. Astronomers also search for biosignatures, like oxygen or methane in exoplanet atmospheres, and even technosignatures, signs of technology like unusual radio signals or atmospheric pollutants. So far, nothing conclusive, but the next generation of telescopes, like the James Webb Space Telescope, already starting to examine exoplanet atmospheres, and future extremely large telescopes on Earth, and concepts like LUVOIR or Habeck space telescopes may sniff starlight passing through alien atmospheres for hints of life's chemistry. Think too about multiple star systems and exotic suns. Could a moon of a giant planet in a binary star system sustain life, getting energy from both its sun and maybe tidal heating? So many possibilities. Bringing it back to philosophy, we've long personified the sun as life-giver. If there are other intelligences, they likely have a reverence or central concept for their sun as well. Many mythologies on Earth worshipped the sun. It's easy to imagine an alien culture might have similar reverence for their star, at least until they develop science to understand it objectively. There's something universal about a living being looking up at the star that gives it life. In science fiction, authors imagine worlds with red suns and how that affects the mood and culture, e.g., Superman's power comes from our yellow sun versus his native red sun. In reality, the physics changes, but life, if it's out there, will adapt to its circumstances. In summary, our sun is one example of a life-sustaining star, but there are many kinds of suns out there. Some provide gentle, steady warmth for eons. Others are more tempestuous or short-lived. When we search for life in the cosmos, we cast a wide net, but certain stars stand out as promising, especially those somewhat like our sun or slightly cooler. The diversity of stars means diversity of worlds, and possibly a diversity of life forms and civilizations, each with their own story, under their own sun. It's a profound thought. Every star in the sky could be someone's sun, the center of their world. Are we alone with our sun, or do some of those distant suns have beings who wonder about the universe as well? We don't know yet, but just realizing the sun is one among billions of suns opens the mind to the vastness of possibility. Orbits and light, the sun's meaning in our lives. Beyond the science, the sun holds a deep symbolic and emotional meaning for humanity. We live bathed in its light, bound in its gravity, and our existence is intertwined with it. It's no surprise that nearly every culture has myths and celebrations revolving around the sun. Let's reflect on some philosophical threads about what it means to live with a sun, to orbit it, and to depend on it. To orbit the sun means we are part of a grand celestial choreography. For millennia, we didn't realize Earth was moving around the sun. When Copernicus and Galileo brought forth that idea, it was revolutionary. It demoted Earth from the center and made the sun the center of our local universe. This was a blow to human egocentrism, but ultimately a unifying perspective. We became one planet among others, all siblings circling the same parent star. In a way, realizing we orbit the sun was a step toward recognizing our commonality with other worlds, and by extension, potentially with worlds around other stars. Orbiting also gives us the concept of the year, one trip around the sun. Our calendars, seasons, agriculture, and rituals are tied to where we are in our orbit: solstices, equinoxes, harvest times. We literally count our lives in orbits. A 30-year-old has gone around the sun 30 times. It's a cosmic perspective on age. Our orbit is also our bond. The sun's gravity holds us. It's a stable orbit, not decaying, not ejecting us. At least, not until the sun changes dramatically. That reliability provides a sense of security in a cosmic sense. We don't feel the motion, but every year we've traveled 940 million kilometers around the sun at about 30 kilometers. It's quite a ride. To depend on the sun is to be aware of our fragility. The sun gives us light and heat. Take that away, and we have nothing. In the far north or south in winter, where the sun disappears for weeks, people historically felt its absence acutely and celebrated its return, hence festivals around winter solstice, like Yule, Christmas, etc., rejoicing that the sun will come back and days will lengthen. Many cultures have sun gods that must be propitiated to ensure the sun rises each day. While we now understand the sun will rise due to orbital mechanics, the emotional relief of dawn each day is perhaps ingrained in our psyche from ancestors who really weren't guaranteed light after darkness without faith or ritual. Even today, sunrise can inspire hope, a new day, new possibilities. Sunset can inspire reverence or reflection, day giving way to night. These natural daily events structure our emotional rhythms. The sun's steadiness gave ancient philosophers a sense of the eternal or divine, yet, as we've learned, even the sun changes and will eventually die. The concept of deep time needed to grasp that is also humbling. It reminds us that even the things that seem forever, the sun rising every day, have a lifespan. There's also a poetic idea. We are children of the sun. Many indigenous peoples figuratively call the sun father or mother. In modern terms, that's scientifically apt. The sun's energy drives photosynthesis, which feeds the biosphere, so the sun is indeed a parent of life on Earth. There's a saying, we are made of stardust, from past star supernovae, and powered by starlight, our sun's rays. The ancient Inca believed they were descended from the sun god Inti. While not literally true, there's metaphorical truth. Life as we know it is a product of this star. The sun also symbolizes enlightenment and knowledge. In the Enlightenment era in Europe, knowledge and reason were metaphorically associated with light, casting away the darkness of ignorance. The sun, as the source of light, became an emblem for clarity, truth, and vision. Phrases like seeing the light mean understanding. Even in cartoons, a light bulb, mini sun, above the head denotes an idea. On a darker note, sun worship in history sometimes led to extreme acts, like the Aztec sun rituals with human sacrifice, believing the sun needed nourishment. This underscores how vital the sun was. They believed without feeding the sun blood, it might not rise or the world could end. That may seem alien to us now, yet in a way, we still sacrifice for the sun, our schedules, our designs, solar panels, sun-facing architecture, even our health. We risk sunburn to enjoy a sunny day. Living in the sun's light has shaped our psychology. Studies show sunlight affects mood, seasonal affective disorder in long dark winters, etc. We crave sunlight. It literally triggers vitamin D production and serotonin uplifts. In literature, a sunny disposition is a cheerful personality. Light is almost synonymous with positivity. There's also the concept of time anchored by the sun. Ancient obelisks and sundials told time by shadows. Our circadian rhythm, internal clock, is tied to the sun. When it's misaligned, like in modern life with artificial light, it can disrupt sleep and health. Thus, the sun still dictates a lot of our biology. In a spiritual or existential sense, the sun reminds us of our place in the universe. Seeing the sun as one star among billions, thanks to astronomy,
has been a profound shift. It tells us we're not the center, but it also tells us the same processes and elements here are everywhere. We share the sun's elements. In fact, the sun and earth formed together. Some find comfort that we come from the cosmos and will return to it. When astronauts went to the moon and looked back, they saw Earth as a small blue orb lit by the sun in the blackness of space. That famous Earthrise photo, taken by Apollo 8 in 1968, is often credited with boosting the environmental movement. Seeing our entire world illuminated by the sun's rays, hanging fragile in space, made people realize our common home needs care. It's poetic that it was the sun's light that made Earth visible and stark against the void, symbolizing how the sun brings not just physical life but also awareness of life's unity. Looking far future again, if humans or our descendants travel to other stars, the sun will become just one star in the sky to them. Imagine standing on an exoplanet around another star, seeing a star that is our sun twinkling among others. How might they mythologize that? It might become the ancestor star or something. Finally, the sun is often used in literature and art as a symbol for constancy. The sun also rises, life goes on. Or for the passage of time, sunrise to sunset as life's journey. It can symbolize power, glory, and even tyrannical heat, as in some desert literature where the sun is an oppressor. In some, the sun's meaning in our lives is multifaceted. Physical nurturer, giver of warmth, light, food, via crops. Timekeeper, day, night, seasons, years. Spiritual symbol of life, resurrection, sunrise each day, sun dying each night, and being reborn. Ultimate reference, we literally revolve around it, reminding us of forces bigger than ourselves. Connector, sunlight connects all life on Earth in a web of energy transfer, and it connects us to the universe, same physics out there. Teacher, studying it taught us science, spectroscopy, heliocentric theory, etc. And metaphorically, it teaches enlightenment. The sun has been constant in human existence. Every human ever has seen the sun, except perhaps a few babies born in polar night who saw it weeks later. That shared experience ties all generations. And yet, we now know the sun itself will change and one day not be there. That knowledge urges us to cherish the daylight we have and perhaps to seek out other stars when the time comes. All told, the sun isn't just a ball of gas out there. It's deeply woven into the fabric of life and thought. It is the light in the sky and the light in our minds when we use it as metaphor. We orbit a star that makes us possible, and in doing so, perhaps we've come to understand a bit of our place in the grand scheme, not at the center, but definitely in the embrace of something wondrous. Final meditation. All life is sunlight, slow and reflected. We began in darkness and came to light. Let's end with a poetic contemplation. The idea that life on Earth is essentially sunlight made flesh. The energy in every heartbeat, every leaf unfurling, every bird in flight, it all traces back to the sun's light. Plants capture photons and fix carbon. Animals eat plants or other animals. We eat and move and grow, all on solar energy. In a phrase, as one scientist put it, we are sunlight, slowed down and walking. That image is profound. You and I are the sun's rays, transformed through the alchemy of life, now thinking thoughts and writing words. In a sense, the sun is thinking and seeing through us. We are a way for a star's energy to know itself. Consider, when you take a bite of fruit, you're consuming the sunlight that orange tree stored. When you take a breath, the oxygen filling your lungs was put into the air by algae and plants using sunlight. When you move your muscles, the calories you burn ultimately came from plants or animals that ate plants, and thus from the sun. Even our fossil fuels are ancient sunlight stored by prehistoric life. We've released a lot of that ancient sun energy, which now warms our climate. In a way, industrial civilization is burning the remains of primeval sunshine, trying to harness as much as we can of that stellar gift. Now we turn increasingly to direct solar power again, realizing the sun gives plenty in real time. We can extend that metaphorically. Art, emotion, civilization, all made possible by the stable climate and food surplus the sun's constancy allowed. In a poetic sense, the warmth you feel in a loving hug or the motion of a dancer is enabled by the sun's sustenance. You could say love and life are the sun's gifts, shaped into something more by Earth's unique chemistry. In ancient traditions, people saw themselves as part of a great cycle, born from Earth under the sun, returning to Earth, with souls perhaps going to the light. In a non-religious but literal way, we do return to the cosmos. The atoms in our bodies will go back to the soil or sea, perhaps to be used by new life, and ultimately some will drift to space when Earth is engulfed or during the sun's nebula phase, and maybe join a new star or planet. Thus the material and energetic cycles continue. The sun will eventually swell and destroy the form of life here, but it will also carry life's building blocks outward. Perhaps by then, life from Earth, maybe in the form of us or future descendants, will have spread to the stars, taking our sun's legacy to other suns. There's a philosophical notion called the Copernican principle. We're not special in the cosmos, but there's also the counterpoint that we are special to each other and in the context of our own planetary system. The sun is not special among stars, but to Earth, it's everything. Likewise, humanity might not be special on a galactic scale, but to our sun and Earth, we matter a great deal. We're the only beings we know that contemplate the sun, after all. In an emotional sense, the sun can inspire awe. Think of watching a sunrise at the ocean, the giant star cresting the horizon, painting the sky pink and orange. It's profoundly moving, often evoking feelings of hope, renewal, even transcendence. That feeling is probably shared by people across time and cultures. It's almost a human universal to be touched by a sunrise or sunset. It reminds us of the cycles of renewal. No matter how dark the night, the sun returns. Now, at the end of our journey exploring the sun, from physics to philosophy, we might appreciate it on an even deeper level. It's not just a glowing disk. It's a long-lived nuclear furnace forging elements and emitting energy that travels 150 million kilometers to make Earth livable. It connects to cosmic events, formed in a nebula, influenced by galactic tides, will eventually disperse into the galaxy. It underpins the existence of every organism and every human endeavor, and it has been a constant backdrop to the human story, watching over us, in a manner of speaking, from our first ancestors to now. The next time you step outside on a sunny day, perhaps you'll remember a fact or two, like, this light took 8 minutes to get here from the sun, and maybe 100,000 years to get from the sun's core to its surface before that. Or, the sun is moving too, orbiting the galaxy, dragging us along at 200 kilometers, and one day it will swell and consume the sky. But also, feel the warmth on your skin and recognize it as the gentle gift it is. We live in the sun's embrace, and as long as we do, we are part of its story, and it part of ours. In the far future, the sun will evolve and shed its earthly children, but by then, perhaps we, or our legacy, will shine under other suns, carrying the flame of life forward. In every beating heart, in every rustling leaf, the sun's energy is at work. In that sense, all life on Earth is a form of sunlight. Sunlight slowed down and transformed into the chemistry of cells and the spark of consciousness. We and our sun are bound together in this intricate dance of energy and matter. So let us appreciate our sun, scientifically as a marvel of nature, practically as the source of our sustenance, emotionally as a symbol of hope and unity, and philosophically as a reminder of both our connection to the universe and the impermanence of even the mightiest things. Every morning when the sun rises, it's a small miracle consistent through deep time. And every evening when it sets, it's a reminder that time passes and nothing stays the same forever. But the cycle gives us day and night, activity and rest, life and growth. In the sky tomorrow, the sun will appear much as it did to the dinosaurs, or to ancient farmers, or to us today, a bright star giving warmth. Billions of years from now, Earth will no longer have such days. But by then, perhaps the legacy of Earth and its life, its sunlight-made life, will have spread to new places, under new suns, keeping alive the memory and substance of our sun in new forms. Our sun's story, from darkness to light, from myth to science, from birth to death and beyond, is ultimately the story of us as well. It's the story of how the universe makes and nurtures and reclaims, a story still unfolding. We are fortunate to witness it from within, to have the chance to understand and reflect upon our sun. In doing so, we come closer to understanding ourselves and our place in this vast cosmos, illuminated by countless stars. And so, as we conclude, we turn our face to the sun, our life-giving star, with knowledge, with gratitude, and with wonder. The day is not done. The journey continues, as surely as the Earth continues its graceful orbit and the sun continues to shine. In the silent depths of space, there are wanderers. From the faintest dawn of history, human eyes gazed upward at bright points of light that moved against the fixed stars. The ancients called them planets, meaning wanderers, imagining gods and myths trailing across the night sky. But beyond the poetry of ancient minds, what truly is a planet? It is more than a mere light in the sky. It is a world unto itself. Planets are the great wanderers of the cosmos, worlds shaped by fire, gravity, and ice, each with its own story, written in molten rock and swirling cloud, in howling wind and drifting snow. They are the children of stars, born from cosmic dust and pulled into spheres by the inexorable embrace of gravity. They orbit in darkness, illuminated only by the suns they circle, and yet each holds its own internal light. The warmth of formation or radioactive decay, the glow of volcanoes, the electric crackle of storms. They range from scorching spheres of rock to bloated giants of gas, from oceanic blue orbs to frozen balls of ice and stone. Some are ensconced in thick blankets of cloud, others naked under the cosmic night. Some, incredibly, are lonely nomads, drifting between stars with no sun to call home, true wanderers in eternal night. To be a planet is to dance in a delicate balance. It means to circle a star in a cosmic rhythm, held by gravity's tether yet ever, falling around the light. It means to be round, sculpted into a globe by one's own gravity, mostly smooth, yet often scarred by the battering of eons. It means to dominate a little corner of space, clearing a path through smaller debris. Planets come in families, solar systems, where each member plays its part in the celestial choreography. Our own family is the solar system, with the sun as the patriarch and planets as its heirs, moving in regal procession. Imagine drifting high above the plane of our solar system. Below, the sun burns as a golden beacon, and around it, like marbles on invisible tracks, the planets sweep through space. Mercury, closest to the sun, is a little burnt cinder racing along its tight orbit. Venus follows, wreathed in thick, toxic clouds reflecting sunlight like a jewel, hiding hellish heat beneath. Earth, our home, blue with oceans and white with clouds, teems with life, our oasis in the dark, Mars comes next, a ruddy desert with ghostly dust storms and polar caps of frost, whispering of a wetter past. Far beyond, a belt of asteroids forms a rough boundary, and then the giants take the stage. Jupiter, king of planets, streaked in bands of stormy color, guards a menagerie of moons. Saturn, with its shimmering rings of ice, elegant and enigmatic. Uranus, tipped on its side, rolling around the sun with a pale cyan hue. Neptune, deep blue and distant, where supersonic winds drive dark storms. And at the edge, small icy worlds like Pluto circle in shadow, blurring the line between planet and comet in the distant Kuiper belt. These are the known members of our Sun's family, 8 major planets by the modern definition, and a host of dwarf planets and countless smaller bodies. Yet planets are not unique to our Sun. As our knowledge grew, we discovered planets orbiting other stars by the thousands. We realized our night sky is filled with other suns, each with their own retinue of worlds. Planets, it turns out, are abundant in the galaxy. Perhaps every star has at least one, and in total, they likely number in the trillions. Some of these exoplanets are familiar in outline, rocky Earth-like bodies or gas giants like Jupiter, but others are stranger than we ever imagined. Giants so close to their stars that their skies rain molten iron, or worlds locked in eternal ice, far from any warmth. There are even worlds that wander alone, rogue planets drifting in perpetual darkness, having been thrown free from their stellar birthplace. The cosmos is literally overflowing with planets of every kind, each a chapter of the grand story of creation. This journey will explore what it means to be a planet from multiple angles. We will trace the historical path, from ancient stargazers to the scientific revolution that revealed Earth as a planet, and the later discoveries of Uranus, Neptune, and Pluto's reclassification, a saga that redefined our cosmic perspective. We will visit the inner solar system, the terrestrial planets, small spheres of rock scorched or nurtured by the sun, each with a unique personality. Mercury's extreme heat and cold, Venus's runaway greenhouse inferno, Earth's living biosphere, and Mars's lost rivers and thin air. Then we venture to the outer solar system, colossal gas and ice giants with raging storms and delicate rings, and moons that might hide life beneath their icy crusts. We will meet the dwarf. Planets like Pluto, Eris, and Ceres, diminutive worlds that challenge our definitions and remind us how diverse planets can be. Beyond visiting each member of our solar family, we will delve into the processes that shape all planets. We'll witness towering volcanoes that spew fire and shifting tectonic plates that mold the lands. We'll examine impact craters, the scars of cosmic bombardment, and winds and water that erode and change landscapes over eons. We'll peer into atmospheres thick and thin, the crushing yellow haze of Venus, the thin cold sky of Mars, Jupiter's banded clouds, and Titan's orange smog. We'll experience weather and climate extremes beyond any earthly storm, from Jupiter's great red spot that has raged for centuries to the 1,200 mile-per-hour winds of Neptune that whip methane clouds into streaks. We will also uncover the hidden magnetic fields and internal structures that many planets possess. Those invisible shields born from molten cores or metallic hydrogen that can deflect deadly solar winds, and the strange interiors where pressures soar and matter behaves in exotic ways. And as our voyage extends outward, we will leave the comfort of our solar system entirely to discover exoplanets in their astonishing variety. We'll classify these alien worlds, super-Earths, hot Jupiters, mini Neptunes, rogue planets, and more, and see how they broaden our understanding of what a planet can be. We'll ponder the conditions that might make a planet habitable, able to support life, and how scientists seek the faint fingerprints of biology on worlds light years away. Finally, we'll look ahead to future exploration, The upcoming missions and bold ideas to visit new worlds, to send robot emissaries or even humans to planets and moons, and to build telescopes capable of reading the atmospheres of Earth like planets around distant suns. And throughout this odyssey, we will reflect on philosophical questions. What do these diverse worlds teach us about our own existence? How has the study of planets changed the way we see ourselves and our place in the universe? In exploring alien worlds, we inevitably hold up a mirror to Earth and to humanity. So, let us begin where our ancestors once did, by seeking to understand the wandering lights in the sky, and in doing so, embark on a journey across the solar system and beyond. Our first stop is the story of how we came to know these planets at all, a tale of curiosity, observation, and the courage to question our place among the stars. From myth to discovery, a history of our understanding.
For most of human history, planets were points of light, their true nature unknown. In antiquity, 5 wanderers were known: Mercury, Venus, Mars, Jupiter, and Saturn. These wandering stars were held as gods. Mercury was the quick-footed messenger, Venus the goddess of love, shining as morning and evening star, Mars the blood, red warrior, Jupiter the king of heaven, and Saturn the god of time. The sun and moon were counted among the planets in the old world view, and Earth was not a planet at all, but the fixed center of creation. In ancient Greece and Rome, and in civilizations as far-flung as Babylon, India, and China, elaborate cosmologies placed these 7 wanderers on crystal spheres or chariots circling the Earth. Their motions were mysterious but meticulously observed. Occasionally, Mars would retrograde, moving backward against the stars, confounding expectations. To ancient astronomers, the planets were divine oracles whose motions foretold omens and seasons, yet their physical nature remained a subject of philosophical speculation. Aristotle and Ptolemy believed in a geocentric cosmos, the planets, sun and moon revolving in perfect circles around an unmoving Earth. It took bold imagination and careful observation to break this geocentric spell. In the 16th century, Nicholas Copernicus proposed a revolutionary idea. The sun, not Earth, was the center, and Earth itself was just another planet circling the sun. This heliocentric model demoted Earth from its special pedestal and made it one of the wanderers. It was a radical, even heretical thought at the time, challenging both scientific and religious dogma. But evidence soon began to accumulate. In 1609, Galileo Galilei turned the newly invented telescope to the heavens and witnessed wonders that forever changed our understanding of planets. He saw that Venus goes through phases like the moon, waxing and waning in shape, which only made sense if Venus orbits the sun, not Earth. He discovered 4 moons circling Jupiter like a miniature planetary system, a clear sign that not everything revolved around Earth. And he observed the rugged mountains and craters on our moon, showing celestial bodies were not perfect ethereal orbs, but had landscapes and geology. Galileo's telescopic revelations gave tangible reality to planets as worlds, places that could be seen and studied, not just lights. With the Copernican paradigm taking hold, astronomers realized that Earth was a planet too, moving through space with the rest. This was a profound philosophical shift. Humanity had to accept that our world was one among many. Over the next centuries, the solar system's known architecture expanded. In 1781, William Herschel, scanning the sky with a powerful telescope, noticed a tiny disk rather than a point. He had accidentally discovered Uranus, the first new planet found in recorded history. At first, Herschel thought it might be a comet, but its slow, steady orbit revealed it as a planet beyond Saturn. The solar system now had 7 planets. The discovery of Uranus doubled the size of the known solar system and suggested there could be more unseen worlds farther out. Uranus's orbit itself held clues of something more. By the early 19th century, astronomers noticed Uranus did not move exactly as predicted. It was being subtly tugged by an unknown force.
Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that an eighth planet must be lurking farther out, its gravity perturbing Uranus's path. In a triumph of physics and astronomy, Neptune was discovered in 1846, almost exactly where the calculations predicted, by Johann Galle and Heinrich Darest at the Berlin Observatory. Neptune was dim and distant, invisible to the naked eye, yet the power of human reasoning had brought it to light. Now the known planetary count was 8. Around the same period, another kind of planet was found in the gap between Mars and Jupiter. In 1801, Giuseppe Piazzi discovered Ceres, a small world orbiting where a much larger planet might have been expected. Soon, Pallas, Juno, and Vesta were found, more small bodies in that zone. At first, Ceres was called a planet, but as dozens more of these objects were detected, it became clear that Ceres was the largest of a whole belt of minor planets, not a lone new world on par with the others. By the mid-19th century, school textbooks briefly swelled the planet count to as high as 11, only to drop back down as Ceres and its kin were reclassified as a separate category. The word planet came to be reserved for the major bodies that dominated their orbits. By the turn of the 20th century, the solar system's 8 primary planets were well known, but some astronomers suspected there might be yet another planet lurking beyond Neptune, Planet X, as it was dubbed. Percival Lowell, an American astronomer, hunted for this theoretical planet in the early 1900s, driven by hints of irregularities in Neptune's motion. Lowell did not find it, but after his death the search continued at Lowell Observatory in Arizona. In 1930, a young astronomer named Clyde Tombaugh systematically photographed the star fields of the ecliptic and painstakingly looked for anything that moved. On a cold February day, Tombaugh found a dim speck that shifted position against the stars. It was the long-sought Planet X, soon named Pluto, after the Roman god of the underworld. The public was enthralled. Pluto was hailed as the 9th planet, a tiny, distant oddball in the solar system's outer reaches. For much of the 20th century, the solar system was taught as 9 planets, Mercury through Pluto. But as telescopes improved, especially towards century's end, we began to find more objects orbiting out near Pluto. In 1992, the first of many Kuiper Belt objects was discovered not far from Pluto's orbit, implying Pluto was not a lone maverick, but part of a larger population of small, icy worlds. The trickle of discoveries became a deluge in the 2000s. Then, in 2005, astronomers announced Eris, an object about as large as Pluto, far beyond Pluto's orbit. Suddenly, our neat conception of the solar system was challenged. If Pluto was a planet, why not Eris? And what about the other large Kuiper Belt objects like Makemake and Haumea being found? The field reached a crossroads. In 2006, the International Astronomical Union took a vote in a meeting that echoed around the world. They formally defined the term planet for the first time. According to the IAU, a planet must orbit the Sun, be massive enough for its gravity to pull it into a nearly round shape, and have cleared the neighborhood around its orbit. By that definition, Pluto failed the third criterion, since it shares the outer solar system with many similar icy objects. Pluto was reclassified as a dwarf planet along with Eris and Ceres. Overnight, the solar system went from 9 planets to 8. The decision was contentious. Many in the public lamented the demotion of Pluto, and even some astronomers disagreed, pointing out that Earth, Jupiter, and others still have small neighbors in their orbits. The debate over what constitutes a planet continues philosophically, but in practice, the new terminology stuck. We now speak of the 8 classical planets and a growing menagerie of dwarf planets. This historical journey, from the earliest recognition of wandering stars, to the Copernican revolution that made Earth a planet, to the telescopic discoveries of new planets, and finally to the reclassification of Pluto, shows how our understanding of planets has evolved with our knowledge. We moved from an Earth-centered universe to a Sun-centered solar system, and then to a vision of countless solar systems in our galaxy. Each step required us to redefine our place in the cosmos, and even as we debated definitions, we learned that nature resists rigid categories. Planets come in a continuum of sizes and orbits. The line between planet and not planet can be blurry at the edges. The story of how we came to know the planets is a story of curiosity, persistence, and a willingness to change our perspective when confronted with new evidence. Having placed ourselves among the planets and traced their discovery, we now turn to explore the planets themselves as worlds. We begin with the inner solar system, those rocky neighbors of Earth that bask closest to the sun's fire. The inner worlds: Mercury, Venus, Earth, and Mars. We begin our planetary journey with the inner solar system, a realm of sun, baked rocks, and metal. These are the terrestrial planets, small, dense, and composed mostly of silicate rock and iron. Born of similar materials and initially not so different, they have since diverged into four dramatically distinct worlds. From airless craters to runaway hothouses to a living blue oasis and a frozen desert, the inner planets show how varied outcomes can be even among sister worlds. Mercury, the closest planet to the Sun, is a little grey furnace of extremes. It is the smallest of the four inner planets, only slightly larger than our Moon. Like the Moon, Mercury's surface is heavily cratered and ancient, recording a violent history of impacts. There are brilliant ray crater patterns splashed across its dark grey terrain, and enormous basins from asteroid collisions long ago. Mercury has almost no atmosphere, just a whisper of atoms blasted off its surface by the sun's radiation, so nothing shields it from meteoroids or evens out its temperature. Daytime on Mercury is blistering, hot enough to melt lead, but the night plunges into frigid darkness since there is no substantial air to trap the heat. A Mercurian day lasts 2 Mercury years long, because Mercury rotates slowly and orbits fast. This results in oddities. If you could stand on Mercury's surface, you would see the sun blazing huge in the sky, rising and setting in a slow, drawn-out dance, even briefly reversing course around sunrise due to Mercury's orbital resonance. Inside, Mercury is a world that punches above its weight. Despite being so small, it is incredibly dense, almost as dense as Earth, because it contains a gigantic iron core occupying most of its interior. This core, spanning about 3/4 of the planet's diameter, generates a magnetic field around Mercury, albeit a feeble one only about 1% as strong as Earth's. Still, it's remarkable that this tiny, slowly rotating planet maintains any magnetic field at all. Mercury's iron heart also hints at a dramatic birth. Perhaps it formed from normal proportions of rock and metal. But a titanic impact early on stripped much of its rocky mantle away, leaving a metal, rich remnant. On Mercury's surface, the evidence of an active past includes long scarps and cliffs, some hundreds of kilometers long and soaring up to a mile high, that crisscross the terrain. These formed as Mercury's core and mantle cooled and contracted, wrinkling the crust above. Volcanic plains, now solidified, also exist, indicating that billions of years ago, lava once flowed across Mercury's surface. But for at least the last few billion years, Mercury has been geologically quiet, a bare, inert world of extremes. It is a planet essentially without air or water, where the landscape is carved only by impact and the slow thermal cracking of sun-baked rocks. In the brilliant morning sun, the ground would be blinding and dead silent, and at night, the stars would burn cold in a black sky over a landscape as still as a tomb. Leaving little Mercury and moving outward, we encounter Venus, often called Earth's twin in size and composition, but in reality, a twisted mirror image of Earth, similar in bulk, yet utterly hellish in condition. Venus is almost exactly the same size as Earth and formed in the same neighborhood of the Sun, presumably with similar ingredients. It likely started out much like Earth, with volcanoes, a thick atmosphere, and possibly even oceans. But at some point, Venus took a divergent path and fell victim to a runaway greenhouse effect. Today, Venus is a world enshrouded in dense, yellowish cloud, its surface hidden from view in visible light. That thick atmosphere is composed overwhelmingly of carbon dioxide, with clouds of corrosive sulfuric acid droplets whipping around the planet. The weight of Venus's atmosphere is enormous. At the surface, the pressure is about 92 times that of Earth's sea level. This heavy blanket has trapped so much heat that Venus's surface is the hottest in the solar system, around 464 degrees Celsius everywhere, day or night, pole or equator. It is hotter even than Mercury, despite being nearly twice as far from the Sun, solely because of the greenhouse gases that lock in the Sun's heat. In essence, Venus shows what happens when a planet's heat balance goes awry. Sunlight passes through the clouds, heats the surface, and the infrared heat cannot escape efficiently due to the CO2, causing a feedback loop of warming. Long ago, Venus might have had temperate conditions, but as the Sun grew brighter over eons, Venus's oceans likely evaporated, and water vapor helped drive temperatures up until the ground itself baked out carbon dioxide from rocks, filling the air with CO2 and turning the planet into a pressure cooker. If you could descend through Venus's clouds, you would find the light growing dim and orange, tinted by the sulfuric haze. By the time you reached the ground, it would be twilight at midday, and the air would be a toxic yellowish fog, so thick it feels almost like a fluid. The heat would be instantly overwhelming, high enough to melt lead, and certainly high enough to melt any lander electronics within an hour or two. The landscape, as revealed by Soviet Venera landers and radar mapping from orbit, is a rolling desert of orange, red rocks, and vast volcanic plains. Venus's surface has mountains higher than Everest and great plateaus, as well as thousands of volcanoes, from huge shield volcanoes to innumerable small cones. The terrain has strange features called coronae, circular patterns hundreds of kilometers wide, believed to be caused by upwellings of magma pushing on the crust. Yet surprisingly, there are few impact craters. The relative lack of craters tells us Venus's surface is geologically young, maybe only 500 million years old. Planetary scientists suspect that Venus underwent a global resurfacing event, perhaps massive volcanism that paved over older terrain, and it may still be volcanically active today. In fact, recent studies of old radar images have shown hints of change in some calderas, suggesting an ongoing eruption, and the Venusian atmosphere contains mysterious chemistry hinting at active volcanoes. However, Venus has no plate tectonics like Earth. Its crust appears to be one giant stagnant lid, which might periodically break down in outbursts of planet-wide volcanism, essentially repaving the planet in floods of lava. Beneath the surface, Venus likely has a metallic core and a mantle similar to Earth's, but unlike Earth, it spins extremely slowly. A Venusian day is 243 Earth days, and curiously, it spins backwards. This sluggish rotation is likely one reason Venus has almost no magnetic field. Without a protective magnetosphere, the upper atmosphere of Venus is constantly bombarded by the solar wind, which slowly strips away lighter molecules. Yet the atmosphere is so thick and heavy that losing some particles to space hardly dents it. Standing on Venus, you would experience a bizarre scene, a dim orange glow in all directions through the haze, the air utterly still near the ground, and a forbidding, silent landscape of rocks and gently sloping volcanic plains. It is an infernal environment, the closest thing to a vision of hell on any planet, and a stark warning of the power of atmospheric chemistry gone wrong. Traveling onward, we arrive at our own planet, Earth. It might seem unnecessary to describe Earth among its neighbors, but viewing Earth as a planet, one of many, is key to understanding what makes it special. Earth is the only planet we know of that hosts life, and not just a few microbes, but a rich biosphere of complexity and diversity, including us, who can marvel at that fact. Several factors conspire to make Earth a haven amid the void. It orbits in the habitable zone of the Sun, where temperatures allow liquid water to persist on the surface. Our planet is just large enough to hold on to a substantial atmosphere, but not so large as to become a gaseous giant. Earth's surface is a mosaic of blue oceans, green and brown continents, and white clouds, a dynamic, ever-changing patchwork, sculpted by both geological forces and living organisms. Unlike the rest of the inner planets, Earth's crust is divided into moving plates, an evolving jigsaw puzzle riding atop the slow churning of the mantle. This plate tectonics is a geological wonder. Continents drift, collide, and separate. Earthquakes rumble along faults. Volcanoes emerge where plates diverge or converge. Over millions of years, this process rejuvenates the surface, builds mountains, and recycles carbon, and may be crucial in regulating Earth's climate over geologic time. Indeed, plate tectonics, with its ability to bury carbon, rich sediments, and then release CO2 via volcanoes, acts as Earth's thermostat, keeping temperatures within a range that allowed oceans to remain liquid for billions of years. Earth's atmosphere is a unique mix: 78% nitrogen, 21% oxygen, plus traces of other gases like argon, carbon dioxide, and water vapor. That oxygen is a direct product of life. Photosynthetic organisms have been exhaling it for eons. The atmosphere is dense enough to buffer the surface from small meteoroids and to distribute heat around the globe, but thin enough that our planet isn't smothered in crushing pressure. It gives us a mild greenhouse effect, enough to keep the oceans from freezing solid, but not a runaway like Venus. And it shields us from deadly solar and cosmic radiation, especially thanks to Earth's magnetic field. Generated by a rotating, convecting liquid iron core, our magnetic field forms a protective bubble that deflects charged particles from the Sun. Where some of those particles do leak through near the poles, Earth offers a dazzling light show, the auroras shimmering green and red in polar skies. Earth's magnetic field, plate tectonics, and moderate atmosphere all work in concert with the Sun's favorable distance to create a stable, life-friendly environment. In that stable environment, water could remain liquid and life could take hold. Life, in turn, transformed the surface and air, covering once barren rock with soil and foliage, and pumping out oxygen to create an ozone layer protecting the surface from ultraviolet rays. From space, Earth is a shimmering blue marble with swirling white weather systems, a striking contrast to the monotonous clouds of Venus or the rust, red dust of Mars. Yet, early in its history, Earth might have looked more like those worlds in some ways. The young Earth's atmosphere had no oxygen and was rich in carbon dioxide and methane. The surface was largely molten at first and heavily bombarded by asteroids, pockmarking it like Mercury. But Earth cooled, oceans formed, life arose, and life's presence terraformed the planet into the benign paradise we now cherish. Earth's geology and biology are deeply intertwined. It is the only planet known where rocks breathe and living creatures move mountains. While Earth has its share of extreme environments, from Antarctica's icy wastes to the Sahara's furnace sands, it remains the gentlest of the inner planets, blessed with liquid water and a breathable sky. It is, simply put, home. And as we study the other planets, we constantly hold Earth as the reference, asking, why is this planet dead or boiling while Earth thrives? The answers inform our understanding of climate, habitability, and the delicate balance that makes our world livable. Stepping away from Earth, we venture back into harsher realms. Mars, the fourth planet from the Sun, has long captured human imagination as a possible abode of life, or at least as a world most similar to our own. It is often called the Red Planet for its reddish-orange hue when seen in the sky, a color due to iron oxide dust coating much of its surface. Mars is about half Earth's diameter and only 1/10 its mass, a modest world that has undergone dramatic change over time. Today, Mars is a cold, dry desert planet. Its atmosphere is a thin envelope of carbon dioxide at less than 1% the pressure of Earth's, essentially a tenuous sky that offers little insulation or protection. Daytime temperatures on Mars near the equator in summer might rise to a balmy 20 degrees Celsius, but at night they plummet far below freezing. At the poles in winter, carbon dioxide from the air freezes directly onto the surface as dry ice, forming seasonal polar caps that sublimate when spring returns. This leads to large seasonal pressure swings and even causes the atmosphere to shift mass between hemispheres, driving global winds. Mars wasn't always so barren. Ancient Mars was more Earth-like. All the evidence we've gathered from orbiters, landers, and rovers tells us that billions of years ago, Mars had liquid water flowing on its surface. NASA's rovers have driven through dry riverbeds and studied layered rocks that formed in long, vanished lakes. We have seen branching valley networks etched into the highlands, immense outflow channels gouged by catastrophic floods, and mineral deposits that only form in the presence of water. Mars today has water too, but it's mostly locked up as ice in the polar caps or underground, and a tiny amount as vapor in the atmosphere. What happened? Mars's grip on its atmosphere weakened over time. Being smaller, Mars lost heat faster than Earth. Its once molten core partially solidified, and the global magnetic field that might have existed early on dwindled away. Without a strong magnetosphere, the solar wind gradually stripped off the atmosphere. Air pressure fell, temperatures dropped, and surface water either froze or escaped into space. Volcanoes on Mars likely vented gas and lava for a time, perhaps providing temporary warmth, but volcanic activity too has waned. The youngest lava flows on Mars are tens of millions of years old, and no eruptions have been observed in modern times. Still, Mars is not entirely static. It has weather. Thin as it is, the atmosphere can stir up winds that raise reddish dust into towering dust devils that dance across the plains, and occasionally into planet-wide dust storms that can shroud the entire globe in haze for weeks. Its sky often has a butterscotch hue due to fine dust suspended in the air. Wispy clouds of water ice occasionally appear, and at dawn and dusk they can catch the sunlight, creating delicate pastel streaks in the Martian sky. Mars also has seasons, similar in cause to Earth's. In spring and summer, the polar CO2 ice caps partially evaporate, exposing underlying water ice. In winter, they grow as CO2 snow falls. On a Martian summer day, you might see frost that formed overnight glinting in the morning sun, or even a hazy, localized dust cloud that could be analogized to a Martian rainstorm of dust. The Martian surface is a study in contrasts. There are immense shield volcanoes on the Tharsis Bulge that dwarf any on Earth. Just off Tharsis lies Valles Marineris, a canyon system so vast it would stretch across the entire United States, up to 4,000 kilometers long, 200 kilometers wide, and 7 kilometers deep. This Grand Canyon of Mars likely started as a tectonic crack when Tharsis uplifted, then was widened by landslides and perhaps erosion. Elsewhere, the northern hemisphere of Mars consists mostly of rolling, lower plains, whereas the southern hemisphere is high, cratered highlands, an indication that something created a dichotomy in Mars's crust ages ago. Scattered across Mars are impact craters of all sizes, some hosting dune fields within them, others showing gullies on their walls that hint at past flows of water or CO2 ice. Unlike the Moon or Mercury, however, Mars's craters often look worn down, softened by wind, blown dust, or perhaps by ice action. There are also curious features, like the mysterious recurring slope lineae, dark streaks on some crater and canyon walls that grow in warm seasons and fade in cold, once thought to be brine flows. Despite its harshness, Mars remains the most potentially habitable planet after Earth. It is cold, but not beyond the tolerance of life. In fact, hardy microbes on Earth survive in Antarctic ice and dry valleys that resemble Mars. It has water ice in abundance, and perhaps liquid water brines occasionally trickling just beneath the surface. In recent years, tantalizing detections of methane in Mars's atmosphere have stirred excitement, since methane can be a byproduct of microbial life. The dream of life on Mars is one of the reasons we have sent so many probes there. From the Viking landers in the 1970s to the latest Perseverance rover drilling samples for a future return to Earth, we have been reading Mars's history like a book written in rock. That story appears to include a long, gone epoch of rivers and lakes, a gradual climate catastrophe, and the transformation into the cold desert we see now. Mars today is a time capsule of planetary evolution, showing us what can happen when a world's fortunes turn for the worse. Its once thick atmosphere is mostly gone. Some of it lies frozen at the poles, some in the ground, and some atoms still drift in space as a tenuous corona around the planet. In sum, the inner solar system presents 4 different fates for terrestrial planets. Mercury is an airless, baked rock, a planet stripped to its core. Venus is a suffocating hothouse under perpetual clouds, a planet where the greenhouse effect ran rampant. Earth is a balanced, vibrant world, a planet just right for liquid water and life. Mars is a once potential Earth that fell into cold desolation, a planet that lost its warmth and air. These worlds teach us about volcanism, climate, and habitability by comparison. Why did only Earth end up with lush oceans and a breathable sky? The inner planets hold the clues in their craters, rocks, and atmospheres. As we leave Mars and venture beyond the asteroid belt, the sunlight fades and an entirely different kind of planet emerges. Titanic worlds of gas and ice, where swirling storms could swallow continents and rings of dust and ice trace cosmic harmonies. Let us now step into the realm of the giant planets, where extremes reach a new level and moons become worlds of their own. Giants of the outer solar system: Jupiter, Saturn, Uranus, Neptune. Passing beyond the asteroid belt, the sun's warmth diminishes and the worlds undergo a dramatic change. Here lie the giant planets, titans composed mostly of gas and icy fluids, with no solid surface to stand on. They dwarf the rocky inner planets in size and mass. Each is like a miniature solar system unto itself, with rings and moons forming complex families. They are planets of colossal storms, deep mysteries, and delicate rings, where the simple word surface loses its usual meaning. Jupiter is the colossus of our solar system, the 5th planet from the Sun, and by far the largest. With a diameter of about 143,000 kilometers and a mass more than twice that of all the other planets combined, Jupiter looms as a great banded sphere of tan, orange, and white. Composed mostly of hydrogen and helium gas, it is often likened to a failed star. It would have needed to be about 80 times more massive to ignite fusion in its core. Instead, Jupiter shines not by its own light, but by reflecting the sun's, and by emitting a bit of heat it retains from its formation. When you gaze at Jupiter through a telescope, you see not a solid surface, but the tops of its cloud decks, organized into parallel bands that wrap around the planet's fast rotating body. Jupiter spins on its axis in just under 10 hours, an incredibly fast rotation for such a huge planet. This rapid spin flattens Jupiter slightly and drives strong jet streams that separate its cloud bands. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a titanic storm roughly 1.3 times the width of Earth that has raged for centuries like a cosmic hurricane. Its brick red clouds swirl counterclockwise in Jupiter's southern hemisphere. Though it has been shrinking in recent decades, the red spot remains an icon of planetary science, a reminder that weather on other worlds can be on a scale far beyond anything on Earth. Jupiter's entire atmosphere is dynamic. Smaller storms come and go, white ovals and brown barges drift in the cloud lanes, and lightning crackles within towering thunderheads the size of continents. Near the poles, Jupiter's Juno spacecraft has revealed clusters of cyclones arranged in geometric patterns. At the North Pole, a central cyclone is encircled by 8 others like a flower of storms, all enduring and maintaining a surprisingly stable configuration. At the cloud tops, the temperature is around 45 degrees, but it grows hotter and denser as you descend. There is likely no sharp surface where gas turns to liquid. Rather, as pressure increases, hydrogen gas gradually becomes a supercritical fluid, and then a weird metallic form in Jupiter's depths. Beneath the storms, Jupiter hides more wonders. Its immense gravity compresses its interior to extreme pressures. Deep down, the hydrogen is squeezed into a state where it conducts electricity like a metal. This metallic hydrogen region, rotating rapidly, is believed to generate Jupiter's powerful magnetic field, the strongest of any planet, with a magnetosphere that extends millions of kilometers and envelops Jupiter's moons. This magnetic field traps charged particles and produces intense radiation belts. It also powers brilliant auroras at Jupiter's poles, glowing in ultraviolet and infrared, far larger and more energetic than Earth's. The interplay of Io's volcanoes and Jupiter's magnetosphere even creates a permanent flow of electric current between them and fills Jupiter's environment with sulfur and oxygen ions that contribute to auroras and radio bursts. Surrounding Jupiter is a retinue of moons, more than 90 known at last count, ranging from tiny asteroid-like rocks to planet-sized spheres. The 4 largest, the Galilean moons, were first seen by Galileo in 1610 and remain some of the most remarkable places in the solar system. Closest to Jupiter orbits Io, a tortured volcanic world. Io is the most volcanically active body in the solar system, its interior flexed and heated by Jupiter's gravity. Its surface is mottled with sulfurous yellows and oranges, and dotted with erupting volcanoes that spew fountains of lava and giant plumes of sulfurous gas that can rise 300 kilometers high. Next out is Europa, a smooth, icy moon slightly smaller than Earth's moon. Europa's surface is crisscrossed with reddish-brown cracks and ridges over a bright white shell of water ice. Almost no craters mar Europa. It's young and active. Beneath that ice, scientists are confident lies a global ocean of liquid water, kept fluid by tidal heating. Europa's hidden ocean, perhaps 100 kilometers deep under an ice crust a few to 30 kilometers thick, makes it one of the prime candidates in the search for extraterrestrial life. Beyond Europa comes Ganymede, the largest moon in the solar system. Ganymede is a frozen world with a mix of old, dark, cratered regions and somewhat younger, lighter grooved terrain from past tectonic activity. It even has its own internally generated magnetic field, the only moon known to have one, hinting at a molten iron core within. And then Callisto, the outermost Galilean moon, an ancient cratered ball of ice and rock that appears to have changed little in 4 billion years. Callisto's surface is saturated with impact scars, a record of the early solar system's heavy bombardment. While not as flashy as Io or Europa, even quiet Callisto might harbor a subsurface ocean, and it has a composition like a primordial mix of rock and ice, a relic of the solar nebula. Each of these moons could warrant chapters of their own, and indeed they will come up again when we talk about habitability and exploration. For now, they underscore Jupiter's role as a mini solar system, a master planet with its own complex gravitational web, shaping the lives of its moons. Jupiter also sports a barely visible ring system, thin bands of dust encircling the planet above its cloud tops. Unlike Saturn's bright icy rings, Jupiter's rings are tenuous and were discovered only when Voyager 1 flew through Jupiter's shadow and saw them glint. The dust likely comes from meteoroid impacts on small inner moons. The rings remind us that all giant planets have rings of one form or another, a natural consequence of having many orbiting bodies and frequent collisions or ice eruptions to supply ring material. Now we move one step farther out to Saturn, the sixth planet from the Sun, often considered the most beautiful. Saturn is a gas giant like Jupiter, but slightly smaller and significantly less massive. In fact, Saturn has the lowest density of any planet, less than water, meaning if you could find a bathtub big enough, Saturn would float. Visually, Saturn is stunning for one reason above all: its rings. Saturn's rings form a broad, flat disk encircling the planet's equator, composed of countless icy particles ranging in size from dust grains to boulders. They sparkle in the sunlight and are divided into several major rings separated by gaps. From Earth, even a small telescope shows Saturn's rings as a separate structure. Up close, they resolve into myriad ringlets, ripples, and braids sculpted by gravitational interactions with Saturn's moons. The rings are extremely thin, only tens of meters thick in most places, despite spanning over 250,000 kilometers in diameter. They are likely relatively young and are slowly evolving. Saturn's gravity is pulling ring material inward, which means the rings may gradually thin out over tens of millions of years. For now, however, they are a breathtaking demonstration of cosmic geometry and physics. A disk of ice grains tracing the invisible lines of Saturn's gravity and rotational balance. Saturn itself, beneath the rings, is often seen as a pale golden globe banded by subtle belts and zones like Jupiter's, but far more muted in color. Its upper clouds are composed of ammonia crystals. Deeper down likely lie clouds of ammonium hydrosulfide and water, but these are hidden beneath hazes. Saturn's atmosphere is colder than Jupiter's, and its weather, while not as vividly colored, can still be violent. Roughly once per Saturnian year, Saturn experiences a great white spot, an enormous storm that erupts and encircles the planet. One such storm was observed by Cassini in 2011. It began as a brilliant white cloud in the northern mid-latitudes and spread into a band that wrapped around Saturn, accompanied by lightning and turbulent swirls the size of Earth, before dissipating. Saturn also exhibits a bizarre phenomenon at its north pole: a long-lived hexagonal jet stream pattern, first noticed by Voyager and later seen in detail by Cassini. This six-sided wave, like flow of clouds, each side longer than Earth's diameter, rotates as a unit around the pole. At the center of the hexagon sits a whirling hurricane, like vortex with an eye several thousand kilometers across. Why Saturn's atmosphere naturally forms a hexagon is still debated. Likely it's a result of a standing wave in the fluid dynamics of its atmosphere at that latitude. Like Jupiter, Saturn radiates more heat than it receives from the Sun, though the mechanism is different. Saturn appears to be undergoing helium rain as the planet cools. Helium condenses out of the hydrogen, helium mixture in the upper layers, and falls inward, releasing gravitational energy as heat. This helps drive Saturn's weather from below. Saturn's magnetic field is strong. Uniquely, Saturn's magnetic field is almost perfectly aligned with its rotation axis, a fact that challenges dynamo theories. Nevertheless, Saturn has bright auroras observed at ultraviolet wavelengths, and its strong field traps some radiation. Saturn's family of moons is rich and varied, more than 80 known moons. The largest, Titan, is one of the most intriguing objects in the solar system. Titan is bigger than Mercury and enveloped in a thick orange haze of atmosphere. In fact, Titan is the second largest moon and the only moon with a substantial atmosphere, even denser at the surface than Earth's, composed mainly of nitrogen with a few % methane. For a long time, that smog hid Titan's surface completely. But the Cassini mission's radar and the Huygens lander unveiled a world surprisingly Earth-like in some ways. Titan has rivers, lakes, and rain, but of liquid methane and ethane instead of water. At Titan's frigid surface temperature of 179 degrees, water is as hard as rock, and hydrocarbons take the role of the water cycle. Dark methane seas dot Titan's polar regions, complete with shoreline features, islands, and possibly waves. There are branching river channels carved by methane rain flowing into valley networks, and extensive equatorial dune fields made of exotic organic sand. Standing on Titan, you would see an orange-colored sky and a dim sun. The air pressure is about 1.5 times Earth's. You could almost fly by flapping wings strapped to your arms, given Titan's dense air and low gravity. It is an alien yet eerily familiar landscape. In fact, perhaps the most Earth-like place in the solar system, aside from Earth itself, albeit at cryogenic temperature and with a completely different chemistry. Titan likely has a subsurface water ocean as well, beneath the ice crust, making it a double world of interest. A possible haven for some form of life in the warm water below, and a laboratory for prebiotic chemistry in the organic, rich surface environment. Another of Saturn's moons has seized our attention, Enceladus, a small ice moon only about 500 kilometers across. Enceladus looks like a shiny white snowball, reflecting almost all sunlight. For years, its smooth, bright surface hinted something was renewing it. The Cassini spacecraft confirmed that in spectacular fashion. It discovered active water geysers erupting from Enceladus's south pole. Dozens of icy jets spray water vapor and tiny ice particles continuously into space, feeding Saturn's faint E-ring and indicating a subsurface ocean of liquid water beneath Enceladus's fractured crust. Cassini even flew through the plumes and detected salts, organics, and tiny grains of silica. In other words, Enceladus has nearly all the ingredients for life: water, heat, and organic molecules, and it's ejecting them into space, begging for further exploration. The surface around the South Pole has tiger-stripe fissures that are warm and flexing with tidal pulls from Saturn, essentially cryovolcanic vents. This little moon, with a global ocean about 30 kilometers distance below an ice shell some 20 kilometers thick, has become one of the prime targets in the search for extraterrestrial life. Saturn's other moons offer delights as well. Iapetus, half of its surface bright as snow and the other half dark as coal, with a unique equatorial ridge that makes it look like a walnut. Rhea, Tethys, and Dione, medium-sized moons, heavily cratered and cut by ancient canyons. Dione might hide a subsurface ocean too. Mimas, with its giant crater, Herschel giving it a Death Star appearance. Phoebe, a retrograde irregular moon perhaps captured from the outer solar system, rich in primitive material. Each moon tells a different chapter of Saturn's story, from formation to capture to geologic evolution. Yet, through it all, Saturn's majestic rings cast their shimmering veil, illuminating the night sides of moons and casting shadows that stripe Saturn's own cloud tops in eclipse season. Beyond Saturn, the sunlight becomes faint. We reach the ice giants, Uranus and Neptune, the seventh and eighth planets. They are called ice giants, not because they are made of solid ice, but because in addition to hydrogen and helium, they contain a higher proportion of ices, water, ammonia, methane, in a hot, slushy, fluid state inside. Uranus orbits about 2.9 billion kilometers from the Sun, taking 84 years to complete one orbit. It's a pale blue-green orb, about 4 times Earth's diameter, and notably tilted over on its side. Uranus's axial tilt is 98 degrees, meaning it practically rolls around the Sun like a ball. This bizarre orientation is likely due to a colossal collision with a protoplanet long ago. The consequence is extreme seasons. Each pole gets 42 years of continuous sunlight, then 42 years of darkness. When Voyager 2 flew by in 1986, it was southern summer, and Uranus's south pole faced the Sun almost directly. Voyager saw a virtually featureless sphere, a smooth cyan disk with only the faintest hints of cloud, bands or spots. Uranus looked like a painted marble, leading many to call it bland. But as Uranus approached its equinox in 2007, Earth, Space-based telescopes and Hubble started seeing